And I think we're live. Let's see that let me do some sanity checks. Okay, so audio working, feedback working. Okay, welcome. We're going to do day 9 of Advent of Code, day 8 of Advent of Code. We'll just dive right into it. Whoever's watching, hi, hello there, welcome. Yeah, okay, so Haunted Wasteland. You're still riding a camel across the desert island when you spot a sandstorm quickly approaching. When you turn to warn the elf, she disappears before your eyes. To be fair, she had just finished warning you about ghosts a few minutes ago. Once one of the camel's pouches is labeled maps. Sure enough, it's full of documents, your puzzle input, about how to navigate the desert. At least you're pretty sure that's what they are. One of the documents contains a list of left-right instructions, and the rest of the document seems to be to describe some kind of network of labeled nodes. It seems like you're meant to use the left-right instructions to navigate the network. Perhaps if you have the camel to follow the same instructions, you can escape the haunted wasteland. After examining the maps for a bit, two nodes stick out: triple A, triple Z. Feels like A is where you are now, and triple Z is where you're headed, probably. Yeah. This format defines each node in the network individually. For example, right, left. Then we've got triple A is what? Triple B. Okay, so these are the child nodes, basically. Starting with AAA, you look up the next element based on the next left-right instructions in your inputs. In this example, start with AAA, and then you go right, choosing the right element of AAA, triple C. Then left means you choose the left element of triple C, which is triple Z. By following the left-right instructions, you reach triple Z in 2 steps. Of course, you might not find triple Z right away. You can run out of left-right instructions, repeat the whole sequence of instructions as necessary. Right left really means right left right left right left right left, and so on. For example, here's the situation that takes 6 steps to reach Z. So we say left left right. So we've got triple A. We go left to triple B, which apparently doesn't matter because triple B is both edges, and then we say left again. We go back to triple A and then back to Z. Okay, so starting at triple A, follow the left-right instructions. How many steps? How many steps are required for each input? Okay. How many steps are required to reach triple Z? So we might need to cycle more than once through the instructions in order to actually get to triple Z. Okay, I think we can try to manage that. So we've got 2 actual examples here, which is quite interesting. But this one is like non-cyclic, and this one is cyclical, right? Or actually, no. This is wait. Let's think about that. So we say we go left to triple B, then left back to triple A, and then right to triple B again, and then we go from triple B left. So we go back to A, and then then we go left again, and then right. Okay, seems good enough. So let's give it a go, I think. Let's look at the puzzle input just to see. Okay, so here we've got a very long ass sequence of instructions, and we've got a very long list of nodes. And we can try to figure this out. So, um, By the way, I see that triple Z here actually always loops back to itself. Is that the case here? If we go for triple Z, triple Z does not loop back into itself, so we need to actually detect it on the first shot, which is just a very good thing to test for. Okay, so with our trusty IDE, we are going to duplicate day 7, say write day 8. Add that to whatever is important here, which is to duplicate this import and duplicate this. So day 8, day 7, and within our enum also duplicate this one. And we've got our scaffolding working. We just need to also duplicate the input, which is day 8, and paste our input into this thing. Okay, so we've got our input working, input set up, and let's start coding something. So we can clear out this function body because we don't need that at this point. And we will start with the parsing thing, which is just actually passing out our input and making our navigation graph. So we clear everything out until the right up until the tests, and we've got tests that we don't need, and these ones we need to firstly actually test them out. So we've got actually 2 pet tests for part 1 today, because we know this input would give us exactly the number 2. And we do have another input, which means we need to test 2 things, which is this one should give us the number 6. Okay, so armed with 2 acceptance tests, this one should go with number 6. And part 2 is still right until this for now. Part 2 is, well, an empty string. Or maybe we should, like, this would unwrap, but basically we won't run part 2 yet. And we can start writing some code. So firstly, we've got a failing test, right? Or, I mean, it won't be failing. Yeah, it will fail, okay? Our assertion is basically incorrect, of course, because we are returning an empty string without doing anything. And let's start by passing the instructions. So first of all, the instructions themselves. So we've got right, left, and we want to basically just have an enum of right, left instructions. So yeah, instructions, that is going to be right, left. And we want to pass these instructions. So first of all, let's pass a single instruction, which is a very a very short thing to do, not at all of this crap. We are going to literally take an input string of length, basically 1. This should be inlined, probably, because it's so small. And we are going to map literally, it's either how do we say not opt, but one of. Okay, so let's actually do that this way. We say one of tag our instruction right, or is that a thing? Like, this or thing is not correct. Okay, and we are missing and it is unhappy because this should be a tuple. Okay, and we can pass the input on that, and we've got ourselves a instruction parser. So this one passes the instruction, like the actual instruction. Let's write a small test for that. So test pass instruction. That's literally going to be this assertion, and we are missing just the function declaration. Let's run that small test. And it says that it's unhappy. Why is that? So this one of doesn't do what I expected to. Interesting. So we should apparently, okay, so apparently I should have done that differently, which is to map this thing. And it's one of tag L or tag R. Yeah, tag left, tag right, and then we are missing the whole thing, which is we are matching on the character. And it says that it is, why is it unhappy? This function takes one argument, but two are supplied. Wait, what? Okay, yeah. Let's rerun that test. And it still says one of isn't happy. So one of is not the right tool for the job, apparently. Let's just see where have I taken it from. One of. Let's look at the actual usage. So they say one of kind ABC applied on B. Okay, so one of A. So do we just say LR like that, not a list? And it says expected char found refster. Okay. So yeah, let's give the compiler a chance to help us by doing this, and we are just going to slap on whatever is needed for this to work. Where's the instruction? We do want like the debug thing here. Okay, so we've got our parser, our instruction parser working. Let's now actually do the instructions, which is well, no, not yet. Fn instructions. Separated list, not separated, just many one. And it is stopping at a new line, so many till actually. So no, actually, no, many one, just many one instruction input vec of instructions. This is literally going to give us the vector of instructions. We should test that as well. So test pass instructions now. This one is going to be LLR, for example. This one is going to be RLRL. And let's we'll let Copilot do the auto completion here because, well, it's a very small assertion. And it says that it is unhappy because of mismatch types. Says, oh, I know, instructions and instructions. Okay, yeah, we need to use the actual function. Okay, so we've got our parser, our instruction parser working. Now let's turn on to actually defining our network of nodes. So how would we define this node? We are going to define it as a dictionary of pairs of, well, nodes. So we are going to basically store these string references. So not references, but copies of this string. So let's do that. We've got our another struct, or not another struct, but we are going to, we need to pass the node map. So let's just pass that. So test and pass node. And a node is looking like so. And we do have, we do need to pass that into something. And that something is going to be, first of all, let's actually define the function node. So node parser is going to take an input string, ref stir, and going to return an iResult of ref stir. That's where the unconsumed input, and not a vector, just a tuple of so how would we want to define this return type? We would want basically a key and two value pairs. And all of them have the same type. So let's just define a type alias of vertex, basically. And that's going to be not a, is it going to be a string? We'll figure out whether it's going to be a string or not, but that's going to be a vertex into a pair of vertices. So this is our return type, and we are going to actually define that. So separated pair, no. Copilot, you are so stupid sometimes. This is not a separated pair even, or maybe it is separated pair, but it's okay. So it's separated by this thing, but this is going to be take 3 chars, so 3 usize. And then we are going to separate by equals, and then we are going to take another separated pair of this thing. Yeah, that's, I think this is correct. Let's actually look at the format. And we are missing the brackets. So Copilot is, for some reason, doesn't see it, but sure. So we've got not a separated pair, but we have that delimited. Not sure, not delimited, sorry, something else, but it is in this module. Not a separated pair, preceded pair. So there's one of these is like especially for brackets, basically. So let's actually look for brackets. So let's search for this thing. So delimited. And that gives us the thing. Okay, so delimited is the thing. So delimited by tag thing, and then yeah, that's it. Then we can drop all of this crap. And that should give us these two, like all of these things. And this won't compile because these are like strings that are allocated on the heap, and these are not. So we'll think about that in a minute. We might want to do like literally a slice of like 3 characters. Yay, type aliases, yes. Yeah, but we are going to probably modify this type alias in a minute, but now we are ready for doing that easily. So yeah, now we can actually test our assertion against this thing. So firstly, we could assert, yeah, this is an empty string, and this has, yeah, I think this is actually correct. Let's actually see if that is working. And it is unhappy because it's missing, yeah, a thing. Okay, and let's run this assertion. And it is claiming that I am not happy. It is not happy. Why is that? And this is an iResult of, let's look at that. Oh, by the way, also this 3 usize seems like a thing that I want to. I might want that to be pluggable later. Actually, no, the puzzle input isn't going to change between parts. So 3 usize is actually the thing. Um, so this one is taking 3 characters, and this one it claims that it's returning. Wait. Use question mark to return the appropriate. Oh, because of the conversion. So it is convertible from refster to string, but it is not happy because of this thing. So we could literally, okay, so I see what they're doing. They're saying, yeah, you can wrap that in an OK and then do the conversion. And that will basically bubble up any errors that happen through the conversion. And why is it question mark operator has incompatible types? Interesting. So the compiler's suggestions were not good enough. Oh, specifically on the internal separated pair? No, line 42 through 50. So let's try to apply this fix again. It does not work. So instead of this thing, let's try to return a ref string because it's immutable, but missing lifetime specifier. So yeah, this is not good. Can we, let's think about how can we convert that easily? So we do want to return these as freestanding variables because we don't want to actually we don't want to keep references around to like the input. Or can we? Is that possible? Because this one is going to escape the lifetime of the input string basically. So this is not good. Or you know what? Maybe we can do that. Let's actually do this. Let's do some lifetimes. So we've got this thing, and now we do need, let's go with ref. Okay, so this one is going to have a lifetime, and ref take a stir. Okay, so we are specifying that these strings have the same lifetime as the input string. And now we could use that, maybe. It's saying mismatched types. And it says result stir stir, and here we don't need to do anything anymore. We can literally just have these. So these references are not going to be okay. Ooh, yes. So we've done some lifetimes. First time in my life that I've used Rust's lifetimes. Ooh, spooky lifetimes. Yes. Yeah, so basically we are asserting that the strings that are being referenced have the same lifetime as the input. So this output is only valid as long as this string is valid, which since it's going to be valid for the entire lifetime of the function, it's not going to escape anything, and that's good. So yeah, first lifetime. Win, score. Um, Okay, so moving on into actually doing the next thing. By the way, this might bite me in the ass right in the next step, but we'll see that in a minute. But this basically means that we don't need to copy all of these strings around for now. We are just referencing back into the same cohesive piece of memory, which is the past string that we just loaded up from the file. Okay, so we've got pass node. Now let's pass multiple nodes. So that's going to be nodes now. And we are going to copy back 2 of these. That's actually copy, yeah, 2 of these should be enough for now. And let's pass 2 strings. And that should be enough for us to actually do this. So we should say nodes, and we don't know this. Oh, this is a to-do, and we do need to implement nodes. So let's implement that. We've got fn nodes, which is going to accept a string input. that's going to be a hash map between a vertex. Come on, we know that's a vertex, and we do know that we are going to need the lifetime specifier again. So we are going to say tick A, and we are going to say tick A on this as well, and this is going to be the same, going to have the same lifetime as everything else. Did I need to do that? I didn't. That's actually, you know what? This is apparently this should just work. It's a ref vertex. Interesting. I'm not sure that's actually correct. So we can do this not in a loop. Oh God, no. This is so ugly. We do want to say, well, that's going to be manyfold, or fold many one, because there's more than one. And we could say hash map of all of that crap. And we could literally just say hash map new, and that is incorrect. This is though. So we could say this thing and let the thing work. And it is claiming that I result hash map star and found change return type of nodes to something. So fold many nodes, and we are inserting KV. So this looks okay. So why is it unhappy? This is a mutable hash map, and we could like copy this whole thing here. Let's actually do another. Let's add another type alias, which is type graph, and that's going to be another thing where we say, yeah, this is a graph, tick A, and this is going to be a graph new. And it claims that V is ref vertex vertex, but found vertex vertex. Interesting. So we do want to pass ownership here. So this is actually going to store not the references, but the actual vertices. There's no need for us to, we do want to pass ownership of these string references. And this one is actually compiling, and this is, let's actually let's test the nodes parser, and that's going to fail on to do because we haven't done anything fancy. It says, yeah, not yet implemented, of course. So let's implement that. So we do know what our expected thing is going to be. So expected is going to be a graph new from iter. That's going to be a vector of AAA. Yeah, that's very, very nice. I really like the fact that Copilot is like learning the ways of Rust with me. Okay, and expected. And this assertion is not working. Why is that? And it says, ooh, I forgot one thing, which is to say this is actually delimited. We are, I forgot to actually pass multiple lines. So this is actually followed by, not followed by, preceded, terminated. Terminated with an optional new line. That is now passing everything. Ooh, yay! Oh my god. I can't believe this is actually working. Okay, so we've got like type aliases with lifetimes, and we are passing nodes correctly. So we've got a way to build the map. We've got a way to pass the instructions. Now all we need to do is actually traverse the graph and count, and hopefully that would give us a way to do this. We need to pass that, like iterate on the graph indefinitely, or I mean, we need to do that until we hit triple Z. So let's do that. In our run thing, we can say let part one sentinel, which is going to just be triple Z. And we don't know what part 2 Sentinel is yet, but we do know that we do need to pass like the full thing. So we do need to basically pass both the instructions. Cycle detection. We are supposed to cycle. We are supposed to cycle until we hit Z. That's the riddle. See this example. In this example, we are given the left, left, right instruction, and this is the map. We are going to go left through B, and then left back to through A, and then going to right through B, and then left through to A again, and then we're going left back through B, and then right to Z, which is our termination. And usually the thing with Advent of Code is that you're not supposed to check for malicious input. This is not going to cycle on forever. If it's cycling on forever, it's your fault, not the inputs. But it is very good. It's a very good question. Like this, like cycle detection is a thing that you should definitely implement if you are running through a graph that is by definition cyclical. But here, since we've got like the instruction, we are basically traversing the graph in multiple different ways. And yeah, we're not going to implement cycle detection. We are going to basically just but by the way, like the cycle detection is just keeping a hash map of the current state in which on the instruction, like we've got our instruction pointer basically on this thing, and we if we are in the same in the same point of the instruction pointer and on the same point of the graph more than once, then we are definitely in a cycle, if I understand correctly. But yeah, instruction pointers and cycle detections, like using cycle detection is a really good idea for an actual graph traversal algorithm. Yeah. So we've got our Sentinel. We do know our starting position, which is AAA every time. So let part 1 start. That's going to be AAA. And we do want to pass both the nodes and the instructions. So let's do that quickly, just because we do need to do that. So function, we've got instructions and graph. And this is going to be a separated pair by not an optional new line, but by an actual new line. Is it more than one new line, by the way? So it is 2 new lines. So instead of, where is it? Oh shit. First of all, okay, let's rename that into graph, because that's our full graph now. And instructions and graph is going to be instructions, new line, new line. So these ones are going to be also terminated by an optional new line. And that is going to consume both new lines, and that's going to probably work. Let's literally test it out, because this is the way of the world. We have to test things. So we are going to take this small example. Okay, so and we are going to write the test for that. So that's going to be test and then function test instructions and graph, and that's going to include both of these. And let's just do this assertion very quickly. Let's see if Copilot got it right. So it says right, left, and then AAA to triple B and triple C, triple B to D and E. I think this is supposed to be correct. Let's just make sure that this instruction in graphing is actually returning a tuple of Vekov instructions and a graph. Yeah, seems legit. So instructions are going to return a vector of things, and yeah, let's run this test very quickly, and if nothing is going wrong, of course it does. Expected function mute, closure, found, result, blah, 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 blah. And it says terminated. Oh, it is unhappy with this thing. So why that? Oh, because I was passing in the input back twice, and that is incorrect. So the compiler is a friend, as per usual. So moving on to actually using this, we see this thing. So first of all, we've got let input instructions graph. Okay, and we've got that. And let's see first of all if this actually compiles just like that. Not because we might have like lifetime problems. So I just wanna catch them early on. Borrow data escapes the body the time of the function. Ooh. Yes, this is what I feared. This unwrap here, this question mark, not unwrap, but if this fails, then this result is going to include the string which has more lifetimes than like has a longer lifetime than this input string. So how can we ensure this is not a problem? This is where actually thinking about lifetimes is going to be a little bit problematic because I don't know like what is the correct way to do that. So let's use Google for this. We've got this thing. We are going to say, actually, you know what? If we say expect and then fail to pass, is that okay? Yeah, it is okay because it says, well, it is now not passing the string back around. It's not doubling the input string back to the thing, which I'm okay with trading off for now and not thinking about lifetimes anymore. We've got what we need to start working. By the way, vector might not be the actual best thing here. We could literally just have like a slice of whatever, but sure, why not? I mean, that's okay for now. Okay, so we've got our graph and we've got our thing. So how do we implement this iteration thing? So I want to cycle through the instructions. So is there a way to literally do cycles? Cycle! Oh my God, is this like an infinite thing? Let's see. So we've got, yes, okay. That's, oh my God, Rust is so nice with the iteration things. Okay, so we are cycling through the instructions and we are going to keep a counter. How do we say that? We say enumerate, and that is our counter. So we are going to start with our position now. Oh my God, this is so nice. And we are starting with, yeah, we are definitely just folding and okay, let's literally, okay, wait, I'm not gonna look at that for now. So we are saying, we've got our current register, which is this thing or something else. And we've got our accumulator, which we don't even need to, do we need to accumulate? Because we just got the enumerator. So we just need to keep track on, we don't need to plus anything. We just need to keep track of I and then return it at the end. Let's think about that for a minute. So we've got our current thing. Do we need to fold? I mean, this is our way to keep state basically. So we can literally either scan or fold. Right? Let's think about that if we've got maybe another thing. So we are cycling through the instructions and we are running until we've got something. And then we basically want like, I mean, we want to find actually. Interesting. Oh, just literally find. We don't need to even to enumerate. Oh my God. So we just say find by predicate, right? Oh, but that would mean that we cannot pass like an initial state very nicely. So no, okay, let's fold. Let's fold. We say fold and then we say part one and we don't keep doing anything about that. Like we don't need to do anything about that. We do need to enumerate. So this is not going to be correct. For now, let's actually do this correctly now. Let's let Copilot like do the thing where it outputs too many strings. So we do say, okay, so we've got our part one start, which is the thing, and we are folding, which is our current, and we don't care about what is distance. No, this is not the thing. We just want to say part one start. This is our initial ref stir, and we have this thing, which is just a ref stir, and we say I and instructions, and all we need to do is say match on instruction. So is there a way to like index into this tuple correctly? Can we literally just say this thing? This is nicer. So like let next be this. Is that a thing? It says expected ref stir found tuple. And that is correct. Wait, not current. No. What is that? No. Just graph on the instruction returns us, gives us the, let's wait. So wait, we do need to say, okay, our current point on the graph, which is basically we start with AAA, and we want to take the next instruction. And it says that it is okay. So this is about the return type now. We are going to literally just so let's think about that. Do we just want to map that every time instead of like doing this thing? I don't know. I'm thinking out loud basically. So we've got our thing, and this is now our next, and we just want to say, first of all, we can say we can return on next variable, but we do need to break at some point. So folding is not going to work here because next because well, it's basically just gonna like loop on the graph indefinitely. And we cannot break out of this like functional fold because it's never ending. So how would we do that? Is there a way to try fold maybe? And then we can like literally throw or something? Or try find. Interesting. Try for each, try reduce. By the way, what would be the difference between fold and reduce? Let's look at reduce. Just because I'm curious, it's not like related. It's not related to the thing. So reduce is going to. This is the same as fold, the first element of the iterator, as the initial accumulator value, folding every subsequent element into it. Okay. So fold lets us define the thing, and iterator like fold lets us define the initial condition, and reduce does not. Okay, so not very interesting. So if we say trifold, though, we could, I don't know, throw like air out indefinite something, or do we want to? How do we stop after cycling through? I mean, we could literally just write that in a for loop. You know what? Let's just do that in a for loop. So we say let's just do that. Life's too short. So we say for not KV but for node in instructions cycle. So that's going to be our instruction. And we are going to claim that we've got, well, let mute node Let mute vertex, actually. Yeah, let's literally call that a vertex, and that's going to be part1 start. And we could say instruction. We could say, yeah, graph node left, right. So that's going to be our current. So let next be graph current instruction. Why index like that? We can literally index like that. Okay, so this is our next. Then we can say if index equals to the sentinel, we break. And the only thing that we're missing now is the counter, which means that we want to do something like we could literally enumerate on this, and we now got also our index of iteration. So we just say I, and we can say let's think about that. How do we extract I out of this thing? We could say, well, yeah, fuck that shit. Let mute count be 0, and when we exit, we just, before we break, we say count equals I exactly. And that should be okay, I think. And this one, we don't care about the rest of the input. And we can return this count as the thing. And let's run this against our part1. And this should, in theory, maybe work. It says cannot index the value of Webster. Why is that? It says cannot access tuple element at variable index. Okay, so let's not take that as a variable index. We can literally just match on this instruction. So we say match on the instruction, and we are going to do this left and right. Okay, I want something a little bit nicer, but this is good enough for now. This should run and test part1. And why is it taking so long? Because we're cycling through infinity. So this is the sentinel, and we are not updating our current thing. So yeah, why should this work? So not let current. Okay, and this should now fail, and it fails by saying 1. Interesting. And that is because we need to start this with a +1, I think, maybe. Would that work? Let's pass the second thing, and then that would give us another. Oh, it passes both assertions. Okay, that's very nice. Okay, so thing is working because we are the count of moves counts the first node as well. So yeah, basically we now have that thing. Okay, we have a solution. Let's try to run that through the actual input. So we say run this. We edit our configuration. We say D8. Apply, run, and that gives us something. And this number is going to be hopefully gold star winning. And we got a gold star. Yay! That's very nice. Okay, let's continue to part 2. So that's a nice victory. Writing tests and like actually having this working is nice. So let's figure out what are the next instructions to do. So here we are. So let's see. The sandstorm is upon you, and you aren't any closer to escaping the wasteland. You had the camel follow the instructions, but you've barely left your starting position. It's going to take significantly more steps than to escape. What if the map isn't for people? What if the map is for ghosts. Are ghosts even bound by the laws of space-time? Only one way to find out. After examining the map for a bit longer, your attention is drawn to a curious fact. The number of nodes with the names ending with A is equal to the number of nodes ending with in Z. If you were a ghost, you'd probably start at every node that ends with A, and follow all of the paths at the same time until they all simultaneously end up at nodes that end with Z. What? For example, LR, 11A, 11B, triple X to blah, 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 blah. Wait. Every node that ends with A. Okay. And every node that ends with Z. Let's actually read that through. Okay, so we've got left, right. Here we are starting at 11A and 22A. And because they both end with A, we follow the instructions simultaneously. Okay, so we've got a vector of, okay, we need to do this basically in parallel. So there are two starting nodes, and we are going to follow them. Repeat this process until all of the nodes you're currently on end with Z. If only some of the nodes end with Z, they act like any other node and you continue as normal. You would proceed as follows. Okay, so how is that going to take a shorter distance? Anyhow, let's look at that. So we say step one, we are starting at both of these. We choose all of the left paths, leading us to 11B and 22B. We choose all of the right paths, and we are led into 11Z and 22C, and that's why we don't stop. Then we say 11B, 22Z. Okay, so basically we just need to have more than one. We need to interpret this graph differently now. That's the way to do it. So our stopping sentinel and our we need to have more than one like seek head. And okay, I think we've got that thing covered. Like we just need to write on different algorithm. So we still have the same graph. We don't need to think about it so much. We do want to write our own like small test for that. So let's copy this thing and add that into our tests. So test part 2, we are passing this in, and we will expect to see 6 steps. So 6. Now that we've got that, let's actually look at that. So this part 1 is just finished. We can extract that into a function, then not think about it again. So let's actually do that. We could say part 1, that's going to be part 1, basically. Oh, and we definitely want to borrow into this thing because we do want to use the same graph and thing for the next thing. So we are going to borrow the instructions in the graph. And hopefully this will still compile and not like be angry at me for ruining lifetimes. Okay, yeah, okay. We're good. Now we could turn our attention to part 2. Feels like at least a common multiplier question. List common multiplier. Interesting. Hmm. That's a very nice way to think about it. I thought literally just doing this parallel algorithm instead of like doing the sentinel every time, and just running through the thing basically instead of like doing this for every starting node, because that means okay. First of all, let's think about that. So we could do that. But I mean, I like this idea. I want to. I thought about brute forcing this, and this is actually like a more algorithmic approach. Um, but what would be more fun to program? One of them would be like reasoning about just traversing the graph from each starting point, and then like finding the cycle, basically. No, but this is not even a multiplier because we are going to we might visit more than two z cycles. I mean, what I mean is that we might have like 20. We are not guaranteed they are unique like there might be more than one node ending with z and the cycle in the full cycle. So we need to keep track of all the possible z cycles that we've got until we see the same node again, which would be a little bit would be kind of terrible to debug if we fail to do so. What do you think? Yeah. So I think just like brute forcing this and like literally just going through traversing through the graph exactly once, and just when we hope hit the whole z vector, we just might win. I mean, we are not guaranteed that this is we don't get this nice guarantee that we've got like these clean paths that don't have any repetitions in them or more than one z in them. Yeah. So let's just do that. I think like scanning through the thing is not like terribly hard. So let's. I vote just doing this. Okay, so we've got back to our run instruction. So now we need to say something else, which is we need to test for starts with A and ends with A. So first of all, let starting so start to starting nodes are going to be graph dot keys wait is it just keys? Yeah, probably just keys. Yeah, the keys is enough to like find everything. So keys ends with A. How did it know ends with A? No one said that. So these are, well, not count. No, not count. Why is it so stupid? Collect. And that's going to be a vector of vertices. So a vec of vertices. And these ones, why is it unhappy? It says collect. Ref still stir. Clone? Collect? No. We need to like deref this or vec of vertices, ref vertices. It's a ref stir. I don't like that, but let's keep going. And if this comes back to bite us in the ass, then we do this. Okay, so we do have our own now. Now we've got our current nodes, so we say current nodes, and that's going to be our starting nodes. Okay. Oh, so we literally just have we just start with part two. Um, that's going to be current then currents. And that's going to be a vec of vertices. And this is going to be a immutable vector because we are going to mutate it a lot. And now we do say we do have our count, which we will do, and we don't need to for vec of instructions. Basically, we are going to we do need like our end condition, basically. So we could implement that as a new function. Let's not think about flow. I really hate the fact that like Copilot is so bad sometimes. So we do have our own graph now. So we just say the same thing. So we say we iterate over the current things. We say iterate. Then we say we map we say graph dot index. This is our thing. Is that the way to do this? I want to index into the instruction, and it says cannot access method on field. Wait, no field dot index on hash map. Is it not? Is it get? It's get. And we do want only the value, so that's okay. That's going to be. It says attempting to access method on as a field or type attempted to get on a method ref salsa. Use parentheses to call the method. Okay, so apparently we need to, yeah, let's just pass it around. So we've got our node that's going to be, and we are going to borrow this thing, and we are going to try to, well, use this to get something. And it says, okay, it's unhappy with the thing that we've got here, which is we need to say that's going to be, and we need to collect that into thing. So current, that's going to be the next thing. Oh, and we do need to literally index into the instructions. So we need to say, we need to do this routing again. So this is a tuple now, and we need to match on that and do something. So we can say match on instruction, and we could do, yeah, we could say graph n collect blah 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 blah. And why is it not happy with the collect thing? And it says the value of ref star cannot be built from an iterator over ref star. Do we need to borrow that like so? Yeah. And that is a new vector, and we are just doing like iterating over it again. I would be so surprised that this actually compiles. Actually, I don't think you can reach two different Z nodes in a cycle. Interesting. In each Z1 and n times n steps, you reach both. I'm still in favor of brute forcing, but interested to know if another solution works. I think the solution would work, but you need to take account like for there is no like one-to-one mapping between one starting node and one Z cycle per instruction per instruction sequence, I think. Because there might be more than two Z nodes in the cycle, which means you need to take that into account. You need to basically just collect all of this possible Z cycles, which mean that you need to find like basically the least common multiplier for all of these, but you have more than one cycle. That's the only thing. So we just need to do that. And because we know how to do cycle detection, we could do that. Like we basically need to cycle for each starting node, do the cycle detection once, run the cycle. You need to take the register all of the Z nodes that you get. And let's think about that for a minute. Would anything behave differently then? No, I think once you've got that this might work. I think it is. I can reason about it for like I can pretend I believe it's working. So we got our next thing, and if it all ends with z, it says count equals +1, and we've got that. So let's return on new count then. So this is going to be let's call that part 2. That's going to be this thing. And we can return part 2, and that's going to be part 1. And now let's actually run this thing, and let's see if like this test is actually failing or not. And it is failing because of no entry found for key. Ooh, interesting. And that is a very interesting thing. So which key? Why doesn't it show me which key? Let's run this with the debugger. And it says we are getting wait, what? Triple A, triple Z, part 1 Sentinel. So wait, current. Which current is it? It says, okay, this current is triple A. And it says we are trying to assign current with another thing. Wait, we are on part 1 again. Why is this failing? So, wait, what? Interesting. So this thing is not part 1 compatible because there are no triple A's and triple Z's. Oh, that's very annoying. So we cannot run this directly. Oh. Okay, so apparently we do need to pass these inputs like separately. So let's protect this thing and just say it is going to. I'm just gonna basically bypass this for now, and then on actually no, that we do need our unit tests working. So if let's go with this. We say match on. Okay. Yeah, match on graph contains key triple A. And that is going to be false 0 and true something, this thing. Okay, so now we've got our thing like protected. We are not running through this. Ooh, and our part 2 test is actually passing. Let's see that we actually got like an assertion. Okay, we've got an assertion going here. So let's try to run that through our actual input. So we go here, we say run, we are compiling, and this runs now. And oh, this is grinding something. This is going to be terrible. It might be forcing us into actually doing the thing where we say, yeah. Basically, it would be very hard for us to know that we are correct right now without actually trying to do cycle detections. So should we? Should we cycle detect our way out of this? Okay. So I'm stopping this because it's taking a while. Let's do cycle detection. So we've got our vector of instructions and we've got our current nodes. So let's keep track of some visited things. So let mute visited be well, it could be literally just a hash set of which type. Let's think about that. So we've got what would be the type of our hash set? It's going to contain, first of all, a usize, which is the instruction pointer. It's going to contain, why is it unhappy? It says wrong number of arguments. Expected 0, found 1. Oh, is that not the place to add this? Or is it here? Okay, apparently, let's add the type hint here. Just hash set this thing. So we've got a tuple of usize and our, I want to say each vertex with the same usize. No, we need to like for the whole state basically. So we need, in order for us to have the whole state, we do need to do something like I want to say like the full vector, which is very very cumbersome. This is a lot to ask for. Is there a better way for us to do this? We could, while this is while I'm thinking about things, let's actually run this in the background. It might just finish. So this is now running. Oh, or maybe we could even run that in release mode, and that would be even faster, like a lot faster. So edit configuration. Oh, it is in release mode. Okay, so let's run that in release mode, and that should be a lot better in terms of like performance. Yeah, let's just run that, and let's try to think about like brute forcing this, and not at least detecting errors in our algorithm. So we do want, well, I want like the instruction pointer, and I want all of the vertices that we're currently visiting in all of these cycles. Let's think about that. Like this instruction pointer basically it tells us where we are within like the cycle of the instruction pointer, which we should be able to cycle as many times as we want. And we do want like the whole state of the vector, or just one vector is enough. I mean, we could literally just have like a visited thing for each key. A map of sets, like, and then we basically can index a bit like for each part of the current vector. Not amazing, but I just don't want like I know we could literally just have like a vector of vertices. If that is hashable even, I'm not sure. But that is quite seems like quite cumbersome to do that. But sure, but why not? So we've got our current and we've got our I. Do we want before or after the cycle? So this is the visit is actually this thing. So this is the visit contains current clone I, then, and it says this is a vec of things, and we want to dereference that. So this should be a vec of string references. And that is going to be let's just let's print line yeah, oh no, basically. Oh no. Okay, so let's see if we've got an oh no here. And it says mute. Is it dead? Oh. So this is actually not, it's not complaining about cycles, which means basically it might be literally an adversarial cycle, which is like terribly, terribly long, and we should be smart about it. So okay, let's actually let's actually build all the cycles and then do the greatest, the least common denominator for all of them. So, okay, so let's actually build out the cycles. So let mute cycles be a hash map, not a hash set. No. That's going to be a hash map between the starting node, the starting vertex, and the ending vertex. And our value is going to be the length of that cycle. So yeah, I think that's going to be a hash map new, and we are going to build this out one by one. And we've got our current things, which we are not going to do now in the same way. Which means we needed to do this in a different way. So we've got our instructions, we've got our graph. We want to say, oh, I didn't start with them. I didn't want to. Okay, so we've got ends with A. That's all of our starting points. So that's going to be starting points. And each one of them is going to have a different thing. So yeah, first of all, part two answer is still quite far away from us. Okay, so starting points. That's going to be ending points as well. Interesting. So we might want to do this. That's going to be actually that's going to be a hash set. That's going to help us because that means we could literally test that ending points thing instead of like comparing the vector every time. That might be nice. Okay, but actually, yeah, I think that this is like collecting that into a hash set that could be a nice thing. And that also, I mean, these are keys, so that's okay. Like they are by definition unique. By the way, keys are a set, maybe? No, they're not. Okay, so for each starting point, there's no need to sort anything. No, we are going to iterate over that. And for each one of them, we are going to actually, let's just do that very, very, let's be sneaky. So we say start, that's going to be a vertex, and we say sentinel. Well, not sentinel, because we do want like all of sentinels. So sentinels. That's going to be a hash set of vertices. Might be a reference and might be a reference. Okay, so we've got our sentinels and we've got our startings, and we are going to borrow everything. And now we can say start is going to be start. So nothing fancy here. And we do want our start sentinel is going to be, no, that's going to be our sentinel. So that's going to be if current, oh, sorry, if sentinels contains current, then count plus plus, blah, 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 break. That's very nice. And that way we could test it out easily. We just need to pass now part one. Triple A hash set new. No, that's from iter, of course, from iter. From iter vec triple Z. Yes, please. So firstly, let's actually run part one by itself. Let's just test it out to see if it's working. If it is, then we've got our cycle detection, and every time we know that we are doing this with doing this correctly. So let's run part one again. Let's test it out. And it is testing out correctly. Okay, that's very good. So that means that we now have like a very nice way to test out all of the cycles. And the only thing that we need to say, we might want to say, instead of like only returning the usize of this cycle, we want to return the graph pair that we've got. So let's do that. That might be very useful. So we can say literally we are returning not only the usize, but we are returning a vertex and a vertex, and that's going to be this thing. And it says missing lifetime specifier. Oh, so sure, yeah, let's add lifetimes. We say tick A and then tick A on this thing and tick A on this thing. And these are vertices from this graph. So that's going to be tick A and tick A. Everything here has the same lifetime. So let's return the actual thing, which is to say, instead of like doing this break, we literally can return current, start current and our I++, and we don't need our mutable thing. And if we go here, we are unreachable. Yeah, that's going to basically if we reach here, then we know that we've got a problem. Once we've got that, we do need to say that's not going to be actually correct. False. So this is going to also be unreachable because we are not going to run this any other way, and we are going to don't care about the first thing, and usize, that's going to be our part one solution. And let's run our part one test again just to be sure, and they are passing. Now we can go back into running our part two test, but now with actual cycle detection. I mean, not cycle detection. We are going to build out all of the cycles. So we might actually not want to. Okay, this actually still assumes that we've got exactly one ending node for each thing, and let's just pretend like everything's okay for now. And if not, then we would need to think a little bit harder. Wait, is this does not still take the instruction pointer into account, or maybe it does? I'm not sure. So for each starting point, we are going to we can map that into well, part one basically, and we do need to actually like take this closure. So we've got our node, and we can take a reference of that and then call part one with a lot of stuff, which is the instructions, the end node, and the starting point. Okay. And it says the function found part one usize. Oh shit. So that's going to be part one solution, and that's going to be the actual part one function. And that is going to, we are going to collect that into our hash set, to our cycles. So for each starting node, we know exactly what are the, not cycles. This is going to be for each starting node, we know the cycle, and that's not good enough. Interesting. So we should start from like from the index, basically. That's not good enough. Okay, so enough code reuse. Let's actually write this down. So I thought about making part one like the also call the solution for part two, but they are significantly different because we do need to do more stuff. So we've got our instructions. We are cycling through them. We are enumerating them. So we've got our index. And we've got our current thing, which is graph.current. We just need to start with, so let's just add another for loop, which is for each starting point. So just starting point. So for starting point in starting points iter current, do this thing. Yeah, exactly. Hopefully Copilot didn't mess up the copying and starting thing. Starting point, and that's our start and our cycles. Okay, so if contains, we are inserting. So first of all, yeah, we don't want to still break, right? So if our ending points contains this thing, then we are inserting our just a starting point current p plus 1. And the only thing that we are missing now is to actually stop on cycles, because we might want to do this one more time. So we want to say if cycles contains key, starting point current, we do want to break. That means we are done with this starting point, and that means we have now populated all of the cycles. So yeah, okay, we've done all of our cycles now. We've used our starting points, we've used our ending points, which is a hash set. This is a vector. This is a hash map between vertex to a U size. So we know all of our cycle lengths. We should have used also the instruction pointer in the key. The instruction pointer is very important because cycles might be different. So let's think about that. The offset might be, yeah, it is with respect to the key, to the instruction pointer. So that means also we need I here and I there. I think that is now the full cycle detection algorithm. Let's think about that. Is that true? So we now have got all of our cycles because we will break once we hit each cycle here. So this will populate everything, and once we've come full circle. What if we've got? Do we have? Is it possible for us to have a never repeating pattern, like an ever repeating pattern? Probably not. Anyhow, this is actually okay, hopefully. And now that we've got our cycles, let's actually do the thing where we say, let's take the least common denominator of that. So at least common multiplier of all of these cycles. Wait. So that is incorrect because we want not just we don't care which end vertex is actually useful. We want the ending vertex we don't care about. We just care about the starting vertex. For each starting vertex, we want to collect all of the possible different cycles, and any one of them is good enough. We cannot satisfy all of these cycles. Interesting. So let's think about that a little more. So we got our starting node, which is the one we care about. For each starting node, we are actually caring about. Okay, so this is the one. We don't care about the current. All we care about is for each starting node and instruction offset, we've got you might want to try to reason about that actually. Let's try to reason about that graphically. So we say we've got let's remove this annoying background, and we've got A, and then we duplicate that, and then we've got B, and then we've got C. Oh, you know what? 1Z, then 2Z, and then C, and let's also have 1A and 2A. Okay, so firstly, let's just do the obvious, like this thing, which is just it might also like contain different cycles, but basically, let's call it this thing. Okay, so let's pretend we've got this. So all we care about is for a given thing, like we don't care whether we land on 1Z or 2Z. All we care about is that we land on any of the Z's when we land on any of the Z's in this cycle. So this one has a cycle of an offset 1 and a cycle of 3. And this one has an offset 2 and a cycle of either 2, not sorry, and an offset 2 or an offset of 3 and a cycle of 5. So like we've got so 1A should point to an offset of 2. So the cycle like the cycle length is always 5, but we've got offsets of well, either 2 or 3. And then 2A points to a cycle of 3. That's the cycle, basically. We don't care about the instructions at this point. All we want to know is the offsets of like the Z's. That's the only thing that's different. So we've got a cycle of 3 and an offset of exactly 1. And that's it. So these are the offsets. Now we need to find like when do these act in unison. So let's think about that. We cannot write that down in a minute, but let's think about that. So each starting point can go with like whatever cycle. So we need to find like, okay, so we need to compute all of the offsets. We need to like count the cycle length for each of these. And then let's think about that. So how do we actually find like so the multiplier here would be, so how do we compute this multiplier correctly? Interesting, because the offset kind of throws me off. So let's literally reason about that. So we say, how would this thing look like? So we've got 1A, B, okay, 1A, B, Z, 1Z, 2Z, C, then 1A, and here we've got 2A, 1Z, that's not a match yet. Then we are going to C, then 2A, again, 1Z, and that's still not a match, so we need to like cycle on. Actually, let's literally have them in the same string. So okay, so we've got this thing, and then 1Z again, and then C again, then 2A. And that's the thing. Yeah, basically this is the cycle. And this one, look at it closely. So we've got this. This is the cycle again. And okay, so we are at offset. So this one hits on 8, basically. Why is it 8? Right? So we've got 1, 2, 3, 4, 5, 6, 7, 8. So they're lining up on index 8. Why is that? So index 8 is what is it? Or wait, is it like let's zero count that, because we have, okay, this is offset 0, offset 1, offset 2, 3, 4, and then yeah, basically this. And this one is it? Oh, it's basically just the modulo and the remainder. Interesting. So we've got like modulo and remainders here. So we've got mod 5, remainder 2 or 3. and we've got mod 3 remainder 1. And we need to line some instruction index at that. So we need to say, we need to find the first I that is mod 5. Mod 5 equals 2, or mod 5 equals 3, and I index mod 3 equals 1. So this is our the thing that we want to actually compute once we've got the cycles and offset computed. And is there a way to walk back from multiple factors back into like the thing? That's literally a hard problem, I think. Like hmm. But this one is actually like very numerically easy. We just need to compute the cycles and we can march forward, and we don't need to do this for every number, right? Let's think about that. So we could And by the way, let's literally plug this question in. Like we've got this nice number here, this nice formula. Let's actually compute like all of these numbers. So we say, first of all, let's literally paste that into our calculator. Okay, so let's open up Python thing. So Python console. Let's open up Python console, and where is it? Python interpreter not selected. Let's select the Python interpreter then. Interp. So interpreter, add interpreter, local, and virtual environment, existing. Yeah, give it to me. Setup tools not found. I don't care about setup tools. What I want is a Python interpreter. New console. Okay. So we've got that, and we just need to say I equals. Okay, so first of all, let's def fi, and that's going to be return all of that. And we can say or, and okay, so we've got our f, and let's go for I in range 10 is enough, as we know. Print f I and fi. Okay, let's run that. It says that index 7 and 2. What? Is that correct? That's not correct. Oh, it is correct. How did I miss that? That's going to be 1z. No, that's incorrect. So I'm definitely wrong somewhere here. Because that is just our starting point is actually okay. So this thing is still incorrect. So why is this not true? Wait, did I do this correctly? Did I actually? Okay, so we've got mod 3 and mod 5. So the number 2 is this one. We say index, like the instruction index claims that when we hit index 2, no, here we are on, okay, so it's, oh, sorry. So since I is starting from 0, so wait, 0 is mod 0, this is mod 1. Okay. And this is starting 0, 1, 2, 3. So how come index 2 here is coming out to true? As do I wait? Oh, I see. This needs to be wrapped in this thing. So would that now work? And now we see that, yeah, okay, so it was just operator precedence bug. Okay, so index 7 is the first one that actually wins. So we could literally find like the first one once we compute all of the cycles. We could compute this by just going through the indices without actually like going through memory, only like testing out all of these modulos. Is there a better way to do this? Probably not. This is actually quite good, and this would actually take into account all of the possible offsets. And the first one that hits, doesn't matter which one is it, between each starting node would be okay. So okay, let's compute that. I love that we have Python to like quickly scratch up the thing that's hard to like scratch up in Rust. Okay, so cycles are no longer, we don't care anymore about our well, come on. So we don't care anymore about the starting vertex. All we care about is the length of the cycle and the offset that it has. So this is the only thing that we want to care about. So we say usize on both, because this is the length of the cycle and the offset that it has, and this is the offset. So let's call that offset. And our we don't care about. Oh, we literally just want to. Let's think about that. Wait, so that's our length, not the. This is an instruction offset. How do we know how? Wait. So we've got our starting node. This is the index of this thing. Oh, interesting. So we've got. I want 2 indices. I want the one post cycle and the one. Let's think about that. Oh, that's not actually modeling everything correctly right now, I think. Because we might have 2 ways to branch out of the same node. But this might be just, we could literally pretend this is like 1A and everything stays the same. Is that? No, it does not stay the same, because right now we are changing the amount of cycles that we have for each time we offset this. Oh shit. Oh my god, this is actually like making me think. Damn. Let's think about that. So for our small scale example, we did have an algorithm that worked, but it was too slow for the bigger one. We could just let it run, but this is probably, yeah, this is kind of bad to just let it run. So first of all, okay, let's just do let starting nodes. We do know exactly what they are. They are supposed to be graph keys filter on starting with ends with a. Yeah. So we've got collect back of vertices. Yeah. Starting nodes. And we do want like all of our cycles. So let's try to collect all of these cycles. It might actually take a while just to collect all of these cycles. I mean, this graph is not that small. Like if we look at that, this is actually this is a very long instruction set. So that means instruction like it would take a while to like loop through all of this and find all of the possible cycles, because of the amount, like the multiplication of this length times basically like the upper bound complexity of this is the length of this thing, which is 270 characters times the length of the graph. And this graph is approximately 730 nodes, and we have multiple things that end with A. Let's just actually how many things we've got that end with A is going to be \w A. We've got 6 starting nodes. So for each 6 so it's going to be, it should be to test everything out. It is going to be let's actually like compute this. It's going to be 6 times 730 times, what was it? 269 characters. So times 269, that's going to be 1,000,000 paths on the graph to test. Like that's the upper bound of like testing all of these. And this traversal is not even like the yeah, this is basically these are all of the possible paths that you could, like all of the possible starting points of each traversal. Of course, it's going to be way lower than that, but that's going to be like, this is basically very prone to explosions. So how are we planning to actually attack this? Could do like the triple for loop, and basically that is going to be very, very helpful. That's even not it, because the cycles might span longer than one cycle. Okay, I'm kind of stuck. We got our starting nodes. And we are going to just, you know what? Let's just do the thing. Let's just say current and let it run. Okay, so let mute current. There is no need to sort. This is going to be our well, this is going to be our index heads, and we are going to iterate over for instruction in instructions cycle, iter cycle, enumerate. Do we need the index? Yeah, we do. We definitely do. That's going to be current equals match on the instruction Oh, that's going to be I and LR. Okay, so we can match on LR. We are going to collect graph K and the place 0. Yeah, that's correct, I think. Why is that? Let's think about that. So we've got current iter map, and it says probably vec of refster. And we want vec of refster. Is that it? No. Graph K. Wait, what? Okay, sorry. So we can literally say, okay, this is our current vertex, and we can say um, match left, right. Graph K. Fuck is K? Found the expected the ref vertex, found ref. Can we just say collect and let the type system sort it out? Yeah, we can, of course. So this is going to always take either the left or the right. And before we actually do the step, we can say if current iter ends with not any, all ends with z, then let mute path to solution equals 0 use size. Well, path to solution equals I plus 1, I think. Or maybe it's I just now that we've done that in the right spot and not before the matching. So let's actually forward the solution in. So test part 1 is running. What? So apparently I've been grinding my computer. It says that it's unhappy with something, and it is with all of this crap. So we can try this thing, maybe collect now. It says left straight bound borrow ref stir, not implement for ref stir. This thing, this thing. And it says iterator changed item to ref stir. Value ref stir cannot be built from iterator of ref stir. Why is it ref stir though? So specify type explicitly, that's going to be a vec of vertices, and that's going to have to live with that. If that's not working, then we are going to need to do something about that. Let's try to borrow here. That's not good enough, not yet. Wait, oh, it does need to be a reference of strings. Okay, so let's look at that. We've got our current vertex, and we need to index into the graph. Wait, let's do that. So we just say so for each one of these, this is actually, I think this looks good, except for the fact that it's not working like compile wise. Let's see. The value of vector cannot be built from elements of type borrow. We are iterating. Oh, that's not the problem. It's here. So we don't need to do this double borrow thing. Not here, at least. Then it's unhappy on this end. And it might be this thing. We might need to like point this. I'm not sure. Let's actually, you know what? Fuck that shit. We are cloning stuff. Right? Cloning is always like the way to escape allied lifetimes. And it says trait bound not satisfied, not implemented for string. What? Who said string? So we've got graph on the current, I don't know why K, but sure. The trait borrow. Oh, is it this thing? Is it like, oh, triple ref. So that's going to be, okay, so we are going to strip one reference right here. Then now it's unhappy because it says iterative item changed to ref stir. And it says, okay, this expression has a type of hash map, ref stir to ref stir to ref stir. That's okay. And this iterator is double ref stir here. So, and then we are, and then it says it's double ref here. Interesting. So how can we approach that correctly? Okay, let mute. Okay, value of collect. Can we point that here? The size type of stir cannot be known at compile time. Map doesn't have a size at compile time. Wait. Okay, this is like Rust compilation whack-a-mole, basically. So firstly, let's do that outside of the thing. So we could say we've got let next be, I mean, left, right be this thing. We don't need to map anything, so we can just say let left right be current iter map on the graph, and we just extract everything from the graph. So that should be the thing. No need to unzip. Oh, so next nodes. So next. Dot collect. Okay, so we've got next. Let's, yeah, should be okay, and that should be a vec of vertex. And these pairs are now, we can literally just match on them and just say, well, current equals to next. And current equals to next, and that should be probably like so. And it says, oh, sorry. Oh, we could unzip that. Okay, that actually is a nice thing to do, which is to unzip, then collect two vectors basically. So we can say unzip, and that would give us two vectors of. So yeah, this is one vector, and we've got another vector of vertices. And then we can say left or right. And that should be a vec of string references. So that's going to be a vertice reference. It says expected vec found unit. Oh, so let current be, yeah, just literally next left or next right. So I think that should do it if it will only compile. Borrow is implemented for std_string. So why is this happening? Just want to advance the graph. So first of all, k ends with blah 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 blah. Current iter all. Solution I. Okay, that's not it. Current iter map. We are mapping on this graph, which is totally a thing. Wait, stir, refster borrowed refster isn't thing. Found refster. Oh my god, so many references. Expected closure this area to be a closure that returns a tuple, but it returns a reference to a tuple. Interesting. So that is a reference to a tuple, and then we can dereference that. Or can we? Interesting. So we definitely want, okay, so we do want this thing to return references. We don't want to do anything fancy, yeah? So why is it so fucking annoying? Can we instead of map, no, want to, okay, fuck that shit. We are going to do in-place mutation because we can. For k and iter match next, yeah. And it says found vertex. Guess what? It's not a vertex anymore. Cannot find value next in this scope. That's okay. And it says immutable borrow occurs here. Okay, so this is not going to work. Is that? So instead of that, we are going to literally, instead of like having this borrow like here, right here, we can say, yeah, current on index mute, that's going to be graph k, just so expected mute found vertex. Current iter item. So that's going to be cloned. Then that's not going to be a problem anymore. Temporary value dropped while borrowed. So don't drop it. Current. Previously, I just had a solution working for that. Why am I like having so much problems? It's literally traverse the arrow of time. So history. History. Go history. local history. Okay, so we've got a lot of things going on here today. So yeah, wow. We've got tests passing for number 2. Okay, seems like a good place to go for. And how did we do that? We said current iter match on map on match instruction, graph, and okay. So current equals current. And that is going to be expected function got instruction. Um, match on instruction. Wait, what? Oh, so instruction is, that means we are, yeah, we need L out here. Okay, so this is now compiling again, which means that we are going to, wait, match on contains key. No, that's not unreachable. That is definitely unreachable. Um, 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 yeah, so since we're not using all of this crap, we could say just usize again, and return usize, which is I+1. We could say literally let alt1 solution be this, and that is going to be okay. So first of all, yeah, tests are still passing. Let's go and test part2 again. It is failing on 5 against 6. Interesting. Why is that? Because we are returning part2. Let part2 solution be, yeah, that should be placed before this thing. Now we've got the tests passing. And now let's just make sure that this is actually making sense. So we say for each of this, we are matching on this instruction. Actually, instead of matching twice, we could literally just match outside of the loop. This is like just cutting the amount of branches. So match on LR, we are going to sort by. Why sort by? Why is this so like terribly terrible? So current is going to be equal to match on this thing. And instead of that, we are going to have this very, very short thing, which is either on graph 0, and that is going to be right here. So print it's a graph 0. And on graph 1, this should just be faster, basically. And all syntax errors. So this should be a little bit faster, I think, just a little bit. But now we've got part2, which is for some reason infinitely cycling. Oh, yes, it is, because I haven't done the algorithm correctly. Okay, so ends with Z, all seems okay. Could also, instead of ends with, which is like, we could say literally at place 2 equals D. This is like this would be way faster because we are not doing like the whole seeking into the thing. It's just gonna work. And it says type star cannot be indexed using integer. Last. Oh, fine. Bytes 2 equals C. And hopefully this will inline to much nicer assembly. And it says also cannot index into value type bytes. Stars. As slice. As pointer, as bytes. That's a ref to a slice. Okay. And it says bytes Z. Yeah, seems good. Okay, so we haven't broken anything. And this should be hopefully a little bit faster just because it uses yeah, should be good. Let's just now run the brute force on day 8 and let's rerun that. Let's try to, I don't know, like kind of know what our progress is. No, not break, but I just wanna print one dot, just so we'll see like how fast are we actually going. Okay, not very fast. Let's go for 1 million instead of. Okay, the fact that we're going so slow that we are not even seeing this dot means that we're having like serious performance problems somewhere here on this traversal thing. So how can we improve this? We could literally open up a profiler. That could be nice, actually. Like how fast is this actually going? Let's go for 1000 just to see like something moving, maybe. Wait, what? So this is not good. Have we gotten to part 2? Print line. Part 1 solution. You're running this. Okay, so we got part 1 solution quite quickly. Then we are not getting into 1000 things, which means okay, something has gone terribly wrong then. We say enumerate after the cycle. Print line print. Just want to see something moving. Okay, so we are running, not very fast, but something is running. So how come we're not seeing this index actually doing the thing that we expected to? For I and enumerate on the cycle. Print the I so What? Let's literally keep track of I externally. We say I here. We are not counting on this. We are actually ignoring this. We are just cycling through. So we've got our instruction. We are saying I plus equals 1. And we don't need to do anything. Oh, that's actually our solution. So just need to, let's call that solution. And we are just going to literally do nothing interesting. Now that we are plusing this correctly, apparently, I'm just not going to care about that. So if not I, part 1, part 2 solution mod big number. Yeah, let's just do. Okay, so we are running. I don't know what our current rate is, but it's not, it doesn't seem very good. What can we do here to actually save this? So we've got this collecting inside inside the loop, inside the hot loop is not good. Is there a better way to actually get that? We're saying on each of these, we are going to extract it from the map. Then we would want to also update that directly. Can we say iter mute? Then we also get mute vertex. And then we could say map into this thing. Ooh, interesting. So we don't actually need, yeah, let this thing, and we can say n equals this. That's going to mutate in place. That's actually good. And that is also going to mutate in place. So let's go with iter mute. That way we are just avoiding all of these crazy allocations. It says that borrow not satisfied. Do we just do this? It says the trait borrow stir stir not implemented for ref stir. Oh my god. Like so. Cannot assign a new variable to immutable borrowed content. Okay, so mute n mute. Ref mute? No. The trait borrow ref star not implemented for ref star. Let's think about that. So this n is a mutable this is mutable now, right? Would this be better in some other way? I'm like not sure. If we clone this, would things like work differently? No. It says this is still a ref string. We need to do something fancy here. Like I really want not to clone things. That's the whole point. So how do people iter-mute things? Let's actually look at that. Iter-mute. We say that we get an element, and we can say map or not map. I guess not map. Then for each element, we could say this instead of map, not fold for each. Oh shit. There. And it is still unhappy. So let's like disassemble this a little bit. A little bit better. So let's actually say let lrn. Yeah, that's good. We are going to literally take only L. And we are missing, yeah, this branch thing. And we don't care about this right. And it is now saying that this is not working. Interesting. So the trait borrow on ref stir. And this n here is actually supposedly, okay, let's actually go again to see iter-mute, which is for element, we are saying arrow element. Okay, we don't need to say mute here at all. And we could say borrow. No, that's not gonna work. And here we need to say probably star, maybe. That's going to be a reference. Then it is unhappy with the next one. Oh, that's very nice. Okay, so we say star. Okay, so now let's try to unfold that back. So we say dot 0 and we say ref, and that is going to be star n equals this. And we could unfold that back into this thing. Okay, so we say ref and star n. And that is compiling now. Interesting. So our build is actually, so the build is working. Now let's rerun that. Oh, we don't need this mute anymore. Stop and rerun. And now this should be a lot faster. Let's say that if solution mod blah blah mod million, then we can print it out. Is it mod? Yeah, 1 million. Stop and rerun. And let's look at this. Okay, this is running a little bit faster. That's nice. So given that this is our status now, do we want to just let it run? Oh, let's actually, before we actually run it on the actual solution, let's run the test again, just to be sure. It is failing the test, which is an important thing to notice. And that is because we don't need a +1 thing, right? Wait, part 2. So part 2 should be 6. Somehow it's 7. So let's look at 7 now, and then we say +1. And if it is this thing, then we break. So yeah, off by 1 classic. So this should also just work now. Yeah, okay. And while this is actually running in the background, what else can we do to actually do this more performance? So this hot loop, of course, the fact that we've got this branch is also probably helpful, very hurtful. You know what? Let's actually again add I here just to be sure that we haven't fucked up anything. So we say I and function, and let's also add I here. And let's rerun that. I just want to see that I is in tandem with this thing. Yeah, okay, so I is actually doing the thing. So we don't need to do all of this assignment all the time. So can just use enumerate, which should be a little bit cleaner. And then we can say, instead of breaking like that, we can say solution I+1. Yeah, that's good. And instead of this, we can now mod on I. What else can we say about this thing except for actually keeping track of I? So this one is actually mutating in place. That means no allocations. This one is iterating and just asking against the actual things. So this might be like a very if we were like on Sealand, we might want to do like align somehow all of the bytes so we can like slice right through them without like doing this iteration over our current, which is a vector of references to strings, which might be located somewhere in the cosmos, basically. I mean, they are references, which means we are dereferencing everything, which might be actually a problem. So it's instead of copying 3 bytes around, we are actually copying 8 bytes of pointers around, which is kind of bad. So cloning might be actually better. So this should be not a, this is a ref of stir. So I want like a concrete vertex. So I want like, I want like 1D reference instead of 2. I want like the vector to be better. So let's have a vector of vertices, which is way nicer. So let's think about that. What kind of type would I like? I would like basically an array of U8s and of size 3. That's like this is the one I would actually want with some lifetime A. Oh, it's actually plain old data. We don't need to do any lifetimes on that. So if we've got an array of 3 vertices, that's enough. So let's try to use this vertex. What would we need to do in order for this to work? First of all, this is now accessible just like that. And in order for us to actually convert this graph into this thing, we want to do something faster. So what would we want to do here? Let's convert this graph. I want like a better graph, basically. So let a compact graph be iterate over the keys and things, and instead of that, we are going to no, that's why is it so terrible? Okay, this is going to be a hash map between our new vertex and a pair of new. Basically, I just want to compare to copy everything to be compact in memory. Instead of like doing all double, everything is now the double pointer walks, which is just terrible in terms of performance. So how do we convert everything? We say graph iter map, and then all we need to say is as bytes collect with this work. We've got our compact graph. And these compact graphs are going to be a lot nicer, I think. So here we've got the same thing, and we say ends with bytes. So that's going to be a slice of U8s. Interesting. So bytes is not good enough, maybe. I'm not sure. So take 3, exactly, right? Slice take. Interesting. And it says that expected stir slice found stir U8. So thing. How would we fix this? Let's try to run the test and then let the compiler guide us through actually fixing this. We see we've got a collection of everything here cannot be built over from ref of stirs. So we need to do something about that. So we are still on the compacting the graph thing. So instead of this reference, we want to actually try and clone everything. So let's do that. And that would mean that we are allowing it to no stop and rerun. Do that. Where's our thing? And it says item changed. Okay, so this is still not good enough. So K has bytes. How do we take this slice correctly? Can we literally just say into wind and wrap? Okay, that's that try into. Seems it might do the thing. Okay. I'm okay with unwrapping everything. Let's rebuild again. And it says that the trait from refstir not implemented. Okay, so instead of that, would say as bytes, and then everything should be okay, maybe. Okay, so we have moved forward. We've got our vec of things. There's crazy. It is a crazy amount of typing to just make this work. By the way, let's actually go to our run thing. Oh, run. How can I see this tab? Appearance. Where is it? Tools. Display. Drag and drop. No, what? Go tool window boss. Okay. So run. It's still running. Okay, that's good enough. So let's try and figure this thing out. So this still won't compile. because our needle is still incorrect. So if we reference that, is that correct? No, it says expected an array of U8s. So how can we make that into an array? So ends with, I want like an array. So that's going to be let dot sentinel be ARR. Is that an array? Be A, and that's going to be our start sentinel, which is an array of U1, and then that's going to be this thing. Starts with borrow this. Yeah. Oh, so we could literally just use this instead inside. Everything would be okay. Yeah. Okay, so we've got our needle right here. And instead of this graph, we want the compact graph. And the compact graph here as well. And this is now our mutable array. We could assign 2. Is that the way to do this at this point? Like so. Interesting. So let's rebuild. And it is claiming that map on. Okay, so we've still got compilers. Interesting. Value of vec u3 cannot be built from iterator slice ref u8. Interesting. What? Ref of slices of. Okay, so this collect. Interesting. So this one is a. Oh, so I want these to be okay. So we need to filter map these. And then actually, yeah, filter, then map, just because we could. Then we can say, yes, slice like that. No, we want copies. Because it's so small, we just want to clone everything. And then rebuild. And it says, remove the thing. It says, okay, so we can access this directly. And let's try to rebuild again. Okay, so we've got our build running and working. By the way, how is this going? This is actually running. I want to maybe run that as well. Like, and we could profile this. Interesting. So maybe let's actually now profile this as well. I don't want to stop and run. I want I want to allow multiple runs. So let's actually do that. So let's allow multiple instances. Yeah, that's the one. Apply. Now we can run that as well. Again. So let's run that. And this is now. Is it faster? Yeah, it is. We could literally time things. But this is faster, which is nice. What else can we do? Yeah, okay. I say profiling. So let's actually profile this. So let's run this through a profiler. And it says that it needs my sudo password, and I will give it the sudo password. And of course, things need to. Okay, and let's stop that. Profiler data ready. Okay, so we know that we've got build hash and collections all thread ID. Okay, main and hash build. So apparently hash. We are hashing a ton of crap. So maybe let's not do this with a hash. Interesting. Yeah, hash one, hasher. Okay, so we are just hashing. We're doing so much hashing that we might want to consider not using a hash. So let's, instead of this compacting it into a hash map, let's actually try to make an array with a lot of dead indices, and then we know that we are okay because we're just indexing into our own thing. So our compact graph is going to be an array of 3 bytes as the key. So 3 bytes is just a number, basically. A small number, but it is a number. So let's think about that. So we've got do we want to actually pass that into a number, or literally just reinterpret the bytes as numbers? Doesn't really matter, but it will matter in the terms of size. But so we've got, what's the maximum size that we've got? We've got the triple Z, so Z in ASCII. 90. So we've got so that's going to be, come on, basically, well, the upper bound on that is basically one shift, like left shift. Is it 24 times? Because we've got 3 bytes, so 16 million. So this is going to be taking 16 megabytes. But then we will have like a very nice lookup table. Like crazily nice lookup table. So let's actually do this. So let I mean, we could try to lower the amount of bits and then lower the amount of memory, but let's actually do this. We've got lookup table, which is going to be an array of type. Let's actually name that directly. So we've got an array of type what is it? We've got the size we know. The size is 1 shift 24. That's our size. And our type is going to it's going to have to be the amount of size that it takes to contain both the left and the right lookup tables. Or actually, we can have literally, interesting, we could literally have this slice here, which is a VTX, an array of vertices, and then we have left and right vertices. So our compact graph is going to be the let's actually initialize that. So let mute and let mute on that. So instead of like doing this thing here, we can say graph iter for each. Actually, we could literally fold that, but this is going to be probably hard to reason about. Let's, because I need to somehow like know where to put the index in. So graph iter for each. I'm just gonna do this somewhat sanely. So we've got KV and we've got left right. And read U32, is that a thing? Is there a U24? There's no U24, right? There's a U24. What? No. Oh, it's the non-pulsing thing. Um, so this is going to basically be. Oh, by the way, we should say this is actually all zero padded by default, just to like not have garbage. Not sure if like arrays are zero padded by default in Rust, but so as bytes, so I want this to be basically passed as a number. Oh, but I cannot. So interesting. Oh, we could say then as bytes as ref read. Like this won't compile, but I will do my best. So this one, let's just rebuild it, and it will say read user info. Yeah, it doesn't, not found. Of course, it doesn't. It's not found. So basically, let A be this thing, but U32 parse from BE bytes. Yeah, sure. That's a U32. And that is going to be good enough. And then we've got let left right. And we've got this. We don't need to do anything fancy, right? Oh, this is actually already bytes. Interesting. So that means we can actually just we pass everything. We don't need to do anything fancy, but this will actually make this bigger. But that would mean that we don't need to initialize this number every time. So let's pay with one more byte. What's one more byte? Yeah, so basically, yeah, we just have this 0 initialized. We don't need to do anything fancy. And here we say this is the variables may be uninitialized. Initialize with default value. Okay. Okay, so we've got everything now set up. So we've got our left and right nodes for every term. So this is our compactest graph at this point. We don't need this compact graph. We don't need it here. And we do want our current things. So let's just actually do this. We say, so how do we know things end with A? We don't at this point. So we do need to somehow know how to, like, we need to know what our numbers look like. So how do we translate that into numerics, to like numerical values? Let's think about that. So we do have our graph right now, which is a vector of whatever, I don't care. This should be a vector of U32s. So we need to do something with them. So let's actually U32 from blah, 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 blah. Yeah, okay. So we've got our vector of U32s. That's our current thing. And this is going to be we do know the size of that. Do we need to do anything fancy around this? No, that's okay. Now, we could say we do have our instruction, which is either left or right. And for each one of them, we are going to just either take the left branch or the right branch. There is no .1 or .2. This is just a number. And we could interleave them, so we will have basically in that way we will be like cache coherent, but that doesn't really matter. By the way, how is our algorithm going? Slowly. Um, so, by the way, if we just take this very, very big number, and we paste it in just to be like kind of sure everything's okay. This is too low. Okay, so we haven't reached our numbers yet. So like I was suspecting we just might have an algorithmic bug, but this scanning is actually somewhat important. Okay, so we've got our current thing, which is basically we are doing this, and we do need to iterate, and we need to like figure out how to test this. So we need to say something like um, um, so how do we mark things that end with Z? Um, so things that end with Z have a very specific number attached to them, which is, oh, we could literally, okay, so um, we can mask it with the byte mask, which is just the first byte, and then it should be the byte Z as U32. Okay. And that means that we are masking the last byte. Yeah, should be good, I think. Let's run the test. So let's actually run that. And it says that it requires something, and we can test it out. So what is this? It claims that this is not anymore correct because let's rerun that. Expected a U8, found closure U8. What? K ends with, wait, K is a vertex. Oh. So actually, now that we know that, we know like all of these things. So firstly, let's think about that. Hmm. So we've got our graph. Here is iterating over the keys. And the key needs to end with something. And that is expected function char found. Oh, might be a string because it's now a string. And it says ref u8 found blah 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 mute. Cannot be indexed by mute. So this is mutable. We need to star that and star that as well. Right? It says the type array u32 cannot be indexed by u32. It needs to be what? Usize. As usize. As usize. It says the test is not passing. Why is that? It says paused by exit unsuccessfully. Sig V. Ooh. That's what happens when we are dealing with crappy stuff. But also, like, I'm surprised Rust actually allows us to segfault without us writing an unsafe line. I'm wondering how did that happen? Invalid memory reference. So where do we use invalid memory? So here we are iterating over this, and that so let's try to actually, okay, wait. These are all letters. That means we are definitely smaller than that. Hmm. So what else can we say about this? Current keys ends with blah 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 blah. So this thing might be not correct. From sure, but that's not correct because we just want to use these as bytes, basically. So from either big endian bytes or like small endian bytes. So from BE bytes, or from LE bytes, little endian or big endian. Which one of them would be the right one? Maybe let's try little endian, and if that won't work, then I'm kind of like mucking around. I'm not doing something fancy. Still segfaults. Wow. So we've initialized everything, right? Have we not? Um, so the fact that we're using hashes might be useful if we just want memory safety. I mean, memory safety is nice, apparently. But I'm surprised that Rust actually segfaults. Okay, so abandon ship, I guess. We could have these as two different hash maps, and that might be a little bit. But would that be nicer to the cache? Yeah, it would mean that we'd need to pull a little bit less data every time. So, but that means this data won't sit on the same page. Might not sit on the same page. I don't know. I have no idea. So we are not mapping anything right now. So yeah, this is just going to go back into something that's going to be a vec of actual vertices, and we needed to map that into bytes, and that still won't work because this is an array of things, and then we need to do something about that, which is I'm getting tired. What shall we do? I'm too lazy. So part one solution is working. Second part solution is not working, and brute forcing it seems to be not nice. So let's not brute force it then, apparently, and just use regular old vertices. And within our graph, we don't need to do anything fancy right now with just this as well. Our graph. A ends with Z. Oh my god. This one is now unhappy because black ref star cannot be built from ref star again. And that is going to be a ref. No, that has to be something. Says keys. So if key ends with, and then we need to map that. Okay, so we are missing one map. Mismatched types. That is now like so. Says found thing, expected thing. Oh, sorry. 0.1, 0.2. Sorry, 0.1. Okay, so our tests are now back to working. But instead of actually doing this traversal this way, got to go. We'll try to catch up. Hopefully, I will be done soon, either by giving up and like having a life, or finishing it. We'll see which one comes first. So, let's think about that. How can we do this more efficiently? We could list out all of these cycles, which could be quite long, but we could do that. So back to our drawing board. What we've got is we can map each node to multiple cycles, basically. And each cycle to an offset. And that is a thing. So yeah, so 1A can point into a cycle of length 5 and an offset of an offset of 2 and 5, or actually no, that's not even correct. So we've got cycle 5, 2, 3, and 4, and also cycle 4, right? With an offset of what is it? The cycle of 2 and 3. So for each one of these, got our own cycles. And actually, have we got more cycles than that? Yes, we do, because obviously we've got, like, this is the minimal cycles. But we do have, like, longer annoying cycles, which are, we'll try to map them out like so. We've got the cycle of like 1A, 2A, 1Z, 2Z, and then if we go back, interesting. So no, as long as we don't branch here, but we could have branched. I mean, what happens if we've got this branch? Like, I haven't done like the full picture. So, what if we got this thing as well? From this node to this node. Now we've got another way to like loop between things, which is totally dependent on the instructions. So how would we know this to be working? Oh my god, I'm tired. Hmm. So I'm still back into the reference of when we are still mapping with the same instruction pointer. Okay, so we must respect the instruction pointer and each node. And then um, while that is running, how is the run doing? Very, very running. Um, feel like I'm missing like a very, very simple, not simple, but like I'm missing the key point here. Let's look at the thing again. I mean, by the way, the fact that this is so like this is still quite compact. If we'd have like a better thing to do, we could try and actually we could literally try. Interesting. So I think I want to do something different, which is, I mean, I think my Rust solution is actually slower than what I could have what I could write in Python, which I know sounds crazy, but I think like all of these referencing things around is like helpful. And I basically want to use just Python's hack with integers, which is integers are fast, very fast. And dictionaries with integers are extremely fast in Python because they are just using the integer as the index, which means that we could give each vertex. Okay, so let's try to do that. that might be actually a good way to do this. So let's actually have a hash map of type U32, which is small, like the smallest we could afford, to let small, let's call that int nodes. This is now going to be a hash map between that and U32s. And we just need a translation table. That's not true. Yeah, that's going to be hash map new for now. And we just need to translate everything. So we need let lut be from of type lut is going to take us from hash map vertex to U32. And that is going to be hash map from ita. Oh, obviously it doesn't understand. Graph keys enumerate. Yeah. So this is our lookup table that's going to be vertex to int, and we want int to vertex is just going to be the reverse. Yeah. No need to mutate anything. I don't know why Copilot is insisting on mutating things. And we've got our int nodes, which is going to now be a little bit more compact. This is going to be, that's going to be graph. Sorry, not graph from ita. No. From ita, graph, ita things, thing. Okay, so vertex to int on all of these. Yeah, that's very good. So we've got our int nodes, which should be a lot faster. And all we need to do now is starting nodes. So let start, let mute current ints. That's going to be the graph, and we are going to end with a, and then yeah, that's going to point into the thing. Met mute. And that's a vec of U32s. That's very good. And our part 2 solution is going to be this thing, and now we're going to iterate over the thing. And sorry, one thing that we're missing is the sentinels. So we need not only the we need let sentinels. That's going to be all the things that end with. That's going to be also that's going to be a stack of U32s. Filter keys, yeah, vertex to int. Okay, so now we've got everything that we need to do this as compactly as possible. We probably won't even need int to vertex, but we will definitely try that. So we've got everything here is sort of like set up. And that is going to be current ints. Okay, so we've got LR. And for each, we are going to do this crazy thing. No, we are not going to do this crazy thing like that. We are going to, instructions cycle. We could also try to compact, like make this instruction thing be more compact, but let's not do that. So we've got iter mute, and then we can say for each n, we can literally say n, not graph, but was our int graph. So that's going to be our int So our int graph, it's the same it only represents things like more compactly. So basically say our int graph at n dot 2, and this one should do the same. So that's all. That's all, folks. So this one should be a little bit faster. And when I say a little bit faster, I mean could be a lot faster. I'm not sure. So here we say that we will count to 2. Let's comment this out for now. And I'm gonna run that on. I'm just gonna run that again. So just one more run. That's building. Ooh, look at that. That's way more nice. Oh my God, compactness in memory is so good. Okay. Okay, I'm gonna stop this. This is now good. Now just isn't holding a candle to actually just doing this in a compact way. And that means that the hashing thing here is like very like we're doing good stuff basically. Okay, so this is better, way better. Can we do better though? Now that we've got this thing, like can we break with like this? We still have like a lot of branching going on here. So can we somehow compact this computation, which is probably where we're spending most of our time now? Sentinels contain thing. So I'm using a vector because I know that Sentinels is a very small vector. And I'm not sure whether actually a set of ints might, I'm not sure like what would be more performant. So let's actually just have maybe we should like literally measure time, but I'm not sure how fast would it be for me to actually do that now. But this is already quite nice. Oh, and actually we can say any not contains. And that would be faster just because we can fail on the first one. So and that's obviously incorrect. Wait, so let's just verify that. So we say if any not contains, then we are breaking not. So let's look at that. So we want to say what's the negative of like what's a better way to test this thing. So let's actually do this Rust break iter cycle, breaking out of iterator. So return control flow break. Interesting. So is that a thing? Okay, so apparently we can literally return a break. So that is useful, very useful, because that means we don't need to like we could maybe do this a little bit more cleanly. Which We still have our jump table, which is kind of like annoying here. But what I want to say is something like we are cycling through this. We are trying to fold. No. So how would we do this? What would be the fastest way to test? Like, basically, I want to say, like, if any of the sentinels that is not like if any of these is not containing, we can say continue. So we could say continue. If any not contains, then continue. Import. So say continue. Then and that should be try something, right? So instructions iter enumerate. And that should be for try for each. Try fold, try for each, yeah, for each basically. Try for each. So we don't need to use this for loop from this side. And we do need this thing. So instead of that, we say break. Well, so break and expected result anyhow, but found control flow. Change type to run into iter. Let's just actually use that. So is it supposed to be just still for each? No. Could be try. Expected result anyhow solution found control flow. Wait, I see. And if we say this, yeah, okay, so try for each now, we can say this. And actually, this assignment is, instead of that, we could literally find the value. So let's, and then we can return it. So instead of this, we can say find, I think, and that would give us an optional item. Try find. As an unstable API. So try fold then. Try fold. And then we just need to pass it along more things, right? We need to say try fold is you know what? I'm like doing too many stuff. So try for each, and then we just need to. I can put this out of the branch, and that is going to help us with not doing like conditional instructions are way more expensive than non-conditionals. So this is going to hopefully help us. Like the branch predictor is going to understand this is going to be happening most of the time. And that is hopefully going to be helpful. So yeah, I think that that's good enough. So let's try running that now. And it says rate bound control flow try is not satisfied. That, so we say break something. Interesting. So break unit and this seems slower. So if iter any not contains, continue. So okay, I think this continue thing is still slower than the actual just the for each thing that we did before. So instead of that, let's go back to apparently for loop. I mean, we could literally just loop. But let's just move on. Okay, we've got our solution, and let's go back to all contains. Then we could try and exit out of this function somehow. Is oh, but we are all the time we are return unit, so this won't end ever. So we must use some kind of like breaking mechanism. So let's go with break again. The break with this thing. And once we've got that, we can say try for each. And says that if maybe missing an else clause, continue. What else can we say here? There are better things that we could do. I think the previous like for loop iteration method was faster, I believe. For I LR in enumerate and that thing now is just a function body. There is no break anymore, so we are just literally just breaking like so. Yes, this is definitely faster. Okay, so which one's slower? This one's wait. Yeah, okay, so this is the slower one, so terminate that one. This one, now let it run. What else can we try to speed up here? Let's actually try to profile that now that we've got everything kind of like working. So we could try and profile this one. So I think this should gather enough statistics. So let's stop that. We've got our profiler. And it says we are spending 100% of the samples on this thing, but it's not saying what. They run. Yeah, but run is like not interesting in this case. Poultry. Ooh, low. So 100% of the time is on stdio print, and then we've got like core iter map adapter, less than 1%, which is not very interesting. So, by the way, is this thing that's a map which we are not looking up through at all? So we are just indexing a lot of memory. But now that we've got that, wait a minute. This is the thing where this hash map now is vertex to int. So int graph is just u to u32, and we know these are just the same nodes every time. So, I mean, we know the max number, basically. So we could, instead of that, do this with a vector, as we said. That could be even faster. But we'll test that while this is still running. Okay, so now we've got that. Let's actually do this with the vector. So int graph. Let's actually do left and right things. So let left the vector of u32s, and that is going to be the graph filter vertex int, and that is going to be exactly like the enumerate thing. Okay, that's very good. Right is going to be exactly the thing, but with vertex right. So graph keys, no, not keys. Oh, come on. So keys, and then we want not keys. We want to iterate over the kv. So kv is iterate over kv, and we want the v dot so yeah, k. So we don't care about k, we do care about v, and here we don't care about v, we do care about k. So wait, no, no filters. What am I doing? It's a map. We just care about the values. Oh, but we do want. Let's think about that. Wait. So we want to use the vertex to int hash map, which gives us already the correct thing. Okay, so sorry, we want range. So 1 through what is it? Iter values max. Unwrap. So this range no, I'm not happy with that. So we've got our graph.keys, and we might want to sort them. So let's actually sort the keys, and then we've got, okay, so let's sorted keys be this thing, and then we need to mute, then keys sort. Okay. Now that we've got sorted keys, we could add them in the same place like every time. So keys enumerate, keys enumerate. So these are the vertices. So sorted keys. So now left for sorted keys map. Then we can say vertex to int. No. So left should be now k graph k 0 vertex to int select k, and right does the same. So now we've got our left and right things as contiguous arrays instead of, instead of doing this on the run. So, and now we don't even need hash maps anymore. We just index into the thing. So instead of all of this crap, we just say left like that and right like that. That's going to run faster now. It says enumerate does not exist on Vector. Sorted keys iter. And it says n.usize. So as size. And it is unhappy because we should say n. Ooh, damn. Okay, so we are now even faster. Okay, so this is a lesson about like performance optimizations. Don't use hash maps when you're doing linear walkthrough, like a lot of walks through memory. Okay, so this is now running so much faster that it might just hit the actual thing. Let's actually run a sanity test, which is this still solves our thing, and it does not. Ooh, we are off by one again somewhere. That is because I'm like constantly moving things all the time. And that should do it, I think. Yeah, and let's rerun this. And let's stop the previous one from running because it's correct and slower. And we could profile that now that we've got something kind of like very cool working. So let's profile this. And profiler attached. And we could stop this. Profiler data is ready. We are spending a lot of things, method list. So we are within run. Okay, we are not actually going anywhere. We are spending very little time outside of this thing, which means that we are probably doing okay. And our call tree is probably also okay. Okay, so the profiler will not let us know what we'll try to, we can like literally look at the like try to perf this, but I think this is good enough for now. Yeah, this is basically just running. I don't know, probably we got a lot faster now that we've done that like in a contiguous chunk of memory. I wonder if we could also do something fancier, like I don't know, some kind of sorting might be helpful. I don't know. I wonder how the how does the memory profile look for now? Looks now. So we are not even using the int graph, which is okay. We've got our left and right things doing really well. We've got our int2 vertex thing, which we don't use. This one is just a hash map that we used once to translate everything, and this is just the sorted keys thing. So what else can we do to make this go faster? So the sentinels are now, we could literally, okay, so they are a vector of compact ints already. We could try and like bitmask them in a very smarty pants way, but that's probably just not good, not interesting enough. Okay, so I think we can just let this cook for now. Iter all. So we could try to invert this now, and it might be faster. So any not contains continue else break. And let's rerun that, but in another tab. Yeah, so right now things are running so fast that in front of our eyes, so it's hard to actually know without actually like timing. We cannot eyeball any more performance. So never mind. Let's just let it run. This one is like running very quickly. So it's actually running so fast that we could like increase the amount of time like between reportings. But I don't know. I think I will just go for a minute outside and like we'll come back in a few minutes and things might be either running or not. We'll see. So be right back. So I'm back. This seems to be just running, grinding away at my CPU. By the way, this is of course not the correct solution, but I'm like too deep into the hole. We can try to make the loop tighter. Will we be able to do that? So let's figure out what can we do to make this even faster. So this instruction thing, instead of it being a left-right enum, which might be optimized into a Boolean, we could literally try to do that. Or maybe actually, you know, I wonder if we could do what if we could do maybe some kind of like fancy caching? Not sure. What could we cache? So if we see the same instruction and input and node, we could cache some kind of number here, maybe. I'm not sure. I mean, we could literally like do like the graph traversal thing, which means that we could do the whole dynamic programming thing, but let's not do that now. What else can we cache and not cache, optimize in this loop? So Sentinels contains, that's maybe the thing that I might be worrying is actually taking time. I mean, it is inlined, but Um, so let's try to look at that function to bool. Okay, sorry. Let's actually optimize this into bool. And if it's going to be a bool, can we use that instead of like this thing? Okay, so Rust enum bool. No, we cannot use a bool as the underlying representation of an enum. Instead, create constants. Okay, so apparently enums are not good enough as bools. So let's actually use enums. So that's going to be our let instructions be a spec of bool is to, yeah, okay, so left false, right true, instructions. Okay, awesome. Now we've got bool, and then we can say literally false, true. This is like not very Rust-like, but it is going to be very compact. So, oh, let's bring that back because we haven't proved this is actually working. So, set up. And this one forces the left-right thing to be as compact as possible, basically. So, first of all, unit tests, because we've changed something significant. And we are okay. Wait, what? Test part 2? Oh, we are printing stuff. Are we? Let's actually look what's going on here. So print part 1, that's okay. And print part 2. Yeah, definitely. So grinding. And let's actually keep maybe the print of part 1 just because it was nice to have it as actually that's not important enough. And that's going to be, well, if yeah, sure, whatever. Okay, so this test is running okay. Now that we've got that, let's actually run this now once more with our bool vector. And it is, by the way, as I for comparison, this is actually counting every millionth. This is counting every 10 millionth. But that's actually hurting our ability to eyeball this. So let's actually try to. Yeah, I have no idea how to eyeball this without actually. We could literally print times. So let's actually do that. So let t equals time t. Duration, timestamp. Oh, interesting, bench. So I'm not sure how to use bench. Okay, so probably not now. I mean, it's probably like the test suite here, so we could bench things, which is nice, but not for us right now. So you've got this. It's grinding away. This one is also grinding away. One of them might just be okay. I don't know. Um, um, Rust TQDM. I wonder if there's like a way to actually do this. Ooh, that seems Rust implementation of Python command line progress toolbar TQDM. Uh, Usage for blah blah and TQDM. Ooh, that would be very nice for us because that means that we are just wrapping an iterator with that, and we could get nice benchmarking speed. So let's literally do that. So if we wrap this iterator with TQDM, we should be able to get something. And this will probably, it says, yeah, we need to add that. So cargo add, I guess. Cargo add TDM. That is going to be very nice. Okay, and we've got that. Now we can import that. TQDM. Downloading crates. Ooh. Reading. Okay. And import. From TQDM, import TQDM. And now let's actually run this again. Filing. Downloading. Okay. Oh, we don't need anymore the grinding thing. So yeah, that's gonna be nicer. Hopefully. And now we've got an actual benchmark. That's nice. So we've got, what is it? 500 million? Yeah, 52 million traversals per second. So now we could actually now that we've got an actual benchmark, we could measure things like should we do this? So any not contains, then continue, else break. That means we are going to basically, as I said, okay, this one is running because I'm letting it run. This one we could try to rerun now. Test if it's actually okay. So it's consistently looking the same. Maybe a smidge faster, smidge faster. But not like, but not a game changer. Um, what else can we say that's like on what else can we have here that's like an optimization? We are cycling through the instructions. We might not want to enumerate them. I don't know. Can we literally just count and then when we break, count? Interesting. So um, ooh, .qdm is actually nicer. Just like it's the same, but it's well cleaner. Has no method, struct enumerate. Scope, yeah, sure. That's gonna just work, right? Build. Definitely works. So unused imports, not unrelated. We don't use int vertex for now, and we don't use int graph at all. Let's keep it as a comment for now. Int graph vertex, right? Okay. Rebuild. Warning. No warnings. That's very nice. And optimized target. I'm just gonna add it here just to see that we're not too high, too low. Okay, that's very good. Okay, so I think this might just run for a while. So since this is the case, and we're not exploding the memory on it or anything, this is just grinding through everything. Maybe I should just let this cook for a while and like we'll just handle it later. Um, um, let's think about that. Food instead of like the amount of sentinels that we've got. Um, Hitter. Um, could if we invert this, we say hitter any so if any not contains basically not contains, then so that's going to be what could be faster here? Well, that's actually not true because like any sentinel might not be contained. They all could end up with the same sentinel. So we need to say if current ints any of them are not contained, then we need to continue. Otherwise, we break. This +1 thing, I believe, is the correct placement. We could, by the way, literally, I think we are just using none and TQDM. Let's try to paste that into Godbolt and actually look at the assembly. That's going to be interesting. So we've got Rust, and we could probably add libraries. So let's add num. No num. Oh, rand vecmap compiling. It says and use of undeclared module num. That's not good. If we ignore all of that and we ignore all of the tests, and we only look at part one, basically. So anything above that, and it's still going to say that the TQDM is not known, so create root solution. Oh, use create solution. So that is going to be both solution thing. And no enum values, no, not all of that. And it says vertex not found in the scope. So check vertex and graph. Probably want these, so let's add them. I'm just passing the time until like this thing grinds to a halt. Have we passed it? Wait. 3. How many digits are there here? 1, 2, 3, 1, 2, 3, 1, 2, 3. That's billion. 24 billion. Okay, and here we've got 1, 2, 3, 1, 2, 3, 2, 3. No, that's 180. Okay, that's still has a long time before the matchup. Yeah, this has been running for a while. So instruction as well. Okay. And it says found blah blah. TQDM. Yeah. So we just need to remove the TQDM method right for now. And anyhow, interesting. So no anyhow result. We just want result. It says error type. So that's going to be just not found. Oh, instructions in graph not found. So that's going to be, how can we actually pull this graph into this? Can we? We could pretend this is actually just getting the instructions in graph right here. So these are the instructions, which is the spec of instruction and graph is also the graph. And we don't need to do anything else. And it says that standard core result, not a type error. So core error, use error, whatever. Dyn, expected, found keyword pub. What? Wait, what? Dyn error. Oh, anyhow, we could add. Interesting. So that is nice. Okay. Okay, so let's bring that back to anyhow. And it says external location anyhow does not exist. Lib anyhow. Okay, what now? Do import anyhow or something? Um, let's say just anyhow. That's good enough. Use anyhow result or result solution. You know what? That's gonna can this be unit? Probably not, right? Because we are probably unwrapping something at some point. Oh, we're not. So that's gonna be just solution. That's gonna be just solution here in the end. And ooh, we've got some thing. Got thing. Okay, we've got a lot of assembly. Oh, god damn, so much assembly. So we've got this thing. How can we find anything here? We cannot, probably. Not really. Could try and like add a function just so we'll have thing. Okay, so this is a lot of hashing. Let's try to find run. So run. Okay, example run. We are pushing a lot of things. We have got a lot of crap. Jump not equal. Okay. What is this? We are XORing things. Interesting. So hash, build hash. I'm still like, okay, can we like literally reveal linked code? Interesting. So that's going to be here. Ooh. Okay, so where's our loop? So we've got jump equal 262. Ooh, okay, we've got many jumps here. How can we index better instead of jumping? These are still running. Oh, damn. Move absolute. So let's think about how can we remove one branch here, which is if we go back to our module, we look at this. Instead of having the left and right be like so, we could try indexing with our left-right instruction, which might give us more cache coherence. So let's try that. We've got our bool, and we want to index into those not with jumps, but with a thing. So Right, it's iter mute left right. So what I want to say is instead of left right, I want like both basically at LR. That's what I want. So let's try after left right, let's say let both be a vec of both. Yeah, seems like a thing. Then it will probably say that. Okay, and then we don't need to match on LR at all. We could say this. And it says this will probably not compile, but let's try to compile that anyway and see the errors that we get. And it says that we are missing something, which is this. Let's build that out. Slice indices are of type usize, 4 ranges. Ref bool is not a thing. Okay, so instead of treating this as a bool, as and that's going to be probably like so. Same rate. I'm surprised. Is it still testing though to be okay? Run the test. Okay, so the test's still working. So the new thing hasn't actually improved performance. It did make this a little bit more compact. Like code-wise compact, not like we got LR and N. Now, what we could actually do the opposite, which is to zip them into not both like that, but both on the other way, which is say I want to zip left right collect into a vec of things. Then let's try that. We just need to flip these around. And that gives us back the same thing, but we are now like doing the offsets hopefully a little bit better. So let's try to rerun that. And it is unhappy because we are missing like a close friends or something. It says that tuple dot thing is not indexable. So instead of tuple, let's fucking do that not with a tuple. So both instead of this thing, let's just add a U32 size 2. A vec of mode 2 U interarrays, and it says that it cannot do that for some reason. Why can't you do that? So first of all, let's actually pass this type not through here, through the type hint there. That would give us a little bit more room to play with things. So it says that cannot be built from iterator of item tuple tuple. Interesting. Rust index into tuple. Maybe just a struct. No, we want something that's like we want the compactness of arrays basically. We are zipping them. We say map to LR. If that is working, then that would be amazing. So, okay. And the tests are even working. Let's try to run that now. And this, by the way, okay, this is still running. This is still running. Nothing fancy or interesting going on. Let's run number 3. And we are still on the same level of performance. So nothing interesting here, which is surprising to me. But sure, whatever, we've got that. But this might be actually more compact in terms of assembly. So let's actually look at that, just because I want to like test my intuitions more than anything. So, oh, we could also remove like the in our thing. Let's actually not look at part 1 just because like it's more assembly to look at. So if we go back to our assembler thing and we basically ignore all that, say this thing, and part 1 solution is just an empty string. Zip not found with scope. So zip use std iter zip. Apparently we need to import that. So we just did. And it says still take UDM back again. Because this does not matter for us. And we've got assembly, right? Yeah, we do. And then we could go into this thing where we go to linked code. And then, okay, so we've got now move from PDI, sorry, move from some pointer, yeah, some register. Leah. Ooh, that's what I wanted to see. You see that? That is basically we are computing the both jumps in one go, basically. So we've got either 8 times that plus whatever that this thing is. All we're missing is the fact that this offset is not really 8 bytes. It's just two options. Either 0 or 1. And this both thing, can we, by the way, can we use 216s instead of U30? That also might be actually very, very good. So if we go back to our ints, instead of U32s, let's actually use U16s. This is going to win us a lot of, well, a lot of space. Since we are just using like less than 700. So I think that might be actually, that might be way better. Let's try that. So this one is we can kill this one, and this one is still running. This one is still running. By the way, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. Here we've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so this one is still way ahead. And let's rerun that now. Build first of all. And it says that U32 items changed. Ooh, let's apparently I fucked up. Vertex. Oh, yeah, this is definitely U16 as well. And U16 as well. Rebuild. And let's run that. What? How is it so consistent? I'm very surprised. This is so consistent. Um, Terminate. I was sure this was actually this would give a speed up, which means I'm missing something important. So we've got both. We are now zipping through all of this. Part 2 solution. We are iterating over this. We are mapping, blah, 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 blah. So a vec of pools. This might be also, let's actually use instead of vector of pools. Not sure. Probably there's a specialized use for that, right? I would assume that there is. So we've got instructions, iter, cycle. Um, so got cargo build. And we can try and run that again. I'm very surprised U16s hasn't actually updated the performance of this at all. This like goes against a lot of my intuitions. We paste that, we delete the PQDM thing again. We go back into this thing. No, sorry, this thing. Go to linked code. Where's our Leah? Yeah, so we've got this load effective address, which is just a very good way of basically computing this thing. Oh, so it did compact this a little bit. Just now it's 4 bytes instead of 8. Interesting. So, but we still have a lot of jumps and a lot of crap here. So for femt. Okay, so this is, where is this? Rust dialog. Okay, so this seems to be, oh, that's the like the drop thing, basically. So this is our hot loop. Leah mov zx copies the content of the source operand, register, blah, 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 into the destination, and 0 extends the value. Interesting. Why do we need to 0 extend the value, though? Then we are adding 2 into what? RD10. So RD10. Oh, 2 is like the size of 2 bytes. Okay, that's our actual iteration of doing D for each. So iter mute. Then we compare this to RDX, which is probably the length of the array. Then if we're done, we are jumping back into this thing, and if we're not done, Then we are jumping into this thing to do this store again. Okay, so seems like very, very reasonable. Of LDI, LDP, and then we actually do the move of like, okay, so this lookup is like, oh, this is hell. This is probably what we're spending most of our time. Okay, so so let's think about that. What can we say? Like, what can we tell this thing to do, to know? What can we hint to the compiler to know to make sure that it actually knows the thing? Oh, by the way, that was a good time to copy this long ass thing, paste it here, and just making sure that we've got our submission. We haven't too low yet. Okay. How many steps does it take before you're only on nodes before ends with C? Interesting. Um, at this point, I might be thinking that this implementation might actually be costing us a little bit of time. Ooh, fetch add atomic. Damn. Okay, that is going to, and that's and sequentially consistent, no less. Oh shit. Um, wait, is that no? That's not within each iteration, right? That's just the ID of the EQDM thing. Wait, what? Item. Okay, no. This is relaxed. This is sequentially consistent atomics. No TQDM for you. Let's just do this. Okay, so we do want to copy one thing out of the TQDM thing, which is we are going to learn how to use Unix timestamps, which is time system time now, T0 and whatever. And all we want to say is let's start the time system time now. Then we could say so that's going to be part 2, whatever. No, just elapsed is just going to be, ooh, elapsed is a thing. Interesting. Duration since. Okay, that's very nice. Elapsed. And instead of elapsed, I just want to actually divide things. So let rate be I F64 as elapsed as sex thing, blah 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 blah. And we've got our println itels per sec. Okay. This might be nicer, hopefully. Let's try to run that. Unused import. Ooh. 3. Okay, so we have now gone 3 times faster just by removing TQDM. And we could still do this, and we would still have our statistics. So we could divide things by 100. No, by 10 million. That should be nicer. A little bit quieter, basically. Yeah, so we are going quite faster. Okay, and now I understand why this is actually lying. Because atomics are here to get you. This one is running still, this one is running still, but they're going to terminate this one and terminate this one. Okay, don't pay the cost of an atomic ant when you don't need to. So now that we've got that, so every 10 million rows, we are actually doing this thing. Okay, I think it's a price I'm willing to pay for now. Okay, so, but this actually means that I can seriously see okay, also, we could let's think about that. How can we move this thing to like not be too hot? Like we still want like our tight loop to be faster, basically. So let's think about that. So current ints. We are mutating them in place, and then we are iterating twice on them. So is there a way for us to not do that? Or maybe how does any work, by the way? As slight is sources. What? No. Any. FN and so this thing is still terrible. Let's think about how can we maybe okay, firstly we can try this thing again and then just only do the break. And let's try to run that and see if we actually now get measurably different performance. And here it's 155 consistently, and here it's 156, 157. Okay, so this one is better performance. Okay, so firstly, okay, we can now actually see like performance differences. That's nice. So we can terminate this one. We do have this one running now. And instead of iter all on this thing, we can try to be a little bit more smart ass about that. So instead of this contains thing, which does a linear lookup, can we have that as another thing? Is we could try to build up an index. So actually, yeah, we can do that. So instead of sentinels as a vector for lookups, a linear lookup, let's actually have it as a vector of all of these. Sorry, sentinels. Okay, so our sentinels, instead of that, we could have that as a vector of bools. And that is the only thing that we need to know about this thing is we just need to know whether it actually, yeah, so we just map that into this thing. So K ends with Z. So this thing, we can literally just look up on, not contains, but sentinels at K. So iter map. So if, well, iter map on sentinels K, so get, would this work? Global. Okay, no, so we do need to do like, that's going to be our current, and that's going to be sentinels current. And this will give us, well, a vector of bools, hopefully. And says that all, so all BB. Yeah, sure. Would this be able to compile to something smaller? I don't know. I want to say basically all truthy. So is there a better way to do this? Think about that. We've got our Boolean things, and I think this should be okay. Let's try to build that first of all and see that something fails, of course. And it says that type bool cannot be used as index U32. And we say, why is that a bool? Nice. Type usize. Wait, what? Oh, cannot be indexed by U16. So this should be as usize. And this is slower. Interesting. And if we, instead of mapping that by something else, which is not all like that, literally dot sum, equals to this length, which we know from the get-go because it's always the same length. So that's going to be our let nodes be this thing, and that's just going to be the same size every time. So we don't need to think about that. And it says sum of size S. So that's going to be a sum of U8. And it says required by iterator sum. Item bool. Oh, interesting. So map sum bool. If it's, let's think about that. So we've got sentinels. So I want to reduce all of that basically. So that's just a Boolean. That's gonna unwrap. Then we've got bool and this Boolean thing. If it's all true, then let's just run that. Okay, so faster than this one, of a still slower than the previous one, which is consistently 153. So we are almost back to previous performance, which is not good because I hoped for this to be faster. So what else can we do about this to make this faster? Blazingly fast. So no nodes, doesn't really matter. So we've got our reducer thing. Oh, by the way, a good thing to test is that this is still actually working. Definitely not. All true. Okay, so maybe this one would be nicer, like that. Okay, what the fuck? We are infinitely looping somewhere. Unrelated to this thing. Just okay, let's kill that anyhow. This one is running, this one is running. Whatever. So if current ends break. But why aren't we seeing anything? Debug this test. And start. Run. Resume. Pause. It says stop. Okay, let's step out. Out. Threads variables. Pause. Dispatch semaphore. Wait. What? So we are somehow hung on some semaphore. Not main. Run. Find wait. Run. I'm surprised that something's broken. We don't need this anymore. We've got all of our sentinels, which are the vector of what map of something ends with Z. And oh, sorted keys. Dot map dot, not k, but graph, not graph. What is it? Not vertex to int, but int to vertex. So that's going to be let int to vertex be this thing. Then we need to say sorted keys. Oh, it's already okay. So it is the key. Okay, so sorted keys ends with okay, not graph keys. Okay, so we've got our sentinels now, which should be working, and it says map exists on blah 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 blah. Keys dot iter then map. Okay, so our tests are now running. Okay, that's very good. And that should be things we try to run. Not this thing, but the thing, the test. Okay, so for some reason this is like actually we see like warm up. That's amazing. But this is still slow. Why is it still slow? Let's try to, as we said before, like reduce that into not an or, but an end loop. All of them need to be, and if all of these are reduced into an option, so we need to unwrap that because always a thing. And let's try that. Building. Okay, that's faster, but still not as fast, or competitively fast, but surprisingly not. We are comfortably hovering, consistently hovering around the 151 million iterations per second. That's very interesting. Let's think we can do this maybe even better. So zero cost iteration. Well, doesn't feel like zero because every time we need to query the length of this. I want this to be like a fixed size array. That's a possibility. Because we don't need capacity. We don't have anything like dynamic around it. So let's try that. So we can say instead of current ints be like that. Let's think about it. What else can we? Already have U16s here, stack of bools. So interesting thing is our sentinels is a vector of booleans, and we are indexing it with an array. That actually getting optimized into a bit thing? Probably not. Like, doesn't seem to be. We could like go with something like perfect hash tables, but that would require put on more thinking caps, which I'm obviously not very fond of these times of day. what else can we say about this? Oh, so here we do know our static length. So let's try to also have a static array then of, well, everything. That means that every iteration is now of known length, like well, not compile time, because, oh, that means we still need to know like the length at runtime, because it's dynamically computed by, well, the thing. So we're just carrying a little bit more capacity, which is probably not a thing, not an actual problem. So yeah, probably not it. Let's actually look at that now with Godbolt, just so we'll see how does the assembly look like, because I'm curious. So we got Godbolt. Paste that in, and that will complain that it does not know use system time. So let's do that. Then it says that I'm missing this thing. Where's our use thing? Use system. And time. Use standard time. Use standard time. And let's look at the assembly again. We've got now this length. Okay, let's go for, what is this code? Okay. So firstly, we've got our mov0. What every time it looks quite different, but where's our Leah? Yeah. That's our add something, that's the iteration. Then we just compare and jump. I wonder if we can like trigger some loop unrolling thing. That might be nice. But probably hard. Then we've got another mov and set not equal and increment rex. Interesting. So this increment should be probably faster than like, what's its name? Where is this? This add two thing. But we do need to add two every time in this iteration, right? Because we are balancing two elements at a time. So that is going to do this. Okay, yeah, this is, yeah. We are bound to use that. Okay, never mind. And then this jump, who jumps this thing? We are jumping to this label from other places. So this is basically, all of these moves are just destruction things. So by the way, where's this assignment? We've got this one. So, ooh, oh my God, this is actually hurtful. Oh, this looks like a very, very, very problematic thing, which is, okay, and then jump equal. Where's this jump equal? What? Print. Oh, what? This is the print. Then we've got inc RCX, then mov, RSI, RSP, blah, 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 move, a lot of stuff. I'm pretty sure all of that is not thing, but what do I know? Move things to RCX. Then we are using RCX here. So we might want to actually use count instead of like this let mute usize thing and increment it every time if this is the thing that actually happens. Let's try to clean that up and see if we actually get anything different. So vertex to int blah 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 blah. So instead of all of that, I'm gonna do something very, very different, which is to extract all of that thing into its own function. We'll call part2. And that is going to be, first of all, we can borrow that because we don't need something fancy. And we can pass that borrow right here. That is going to make our life a little bit more nice and cleaner. And apart from that, let's actually literally return I plus 1. That's it. No mute thing. We're just muting this only once when we need it to. And unreachable. Now, let's pop that into Godbolt and see if we've got anything fancier. So we've got our done solution. Let's set up all of this thing. Basically say sorted keys. Yeah, pop that in. And it says that part1 redefined here. But it expected solution. What did it find? Part2. Part2 to string returns usize. Let solution says what it says. Oh, right. We are lying to Godbolt that we're not returning a result. And what does it say? It says closing the limiter. Oh, okay. So now we've got that. Now we can literally go to part2. Is it inlined or something? So first of all, let's actually go to this link code. And so this is the mov of the thing. Mov edx, where's the add? Okay, so we've got n. Ooh, interesting. What are these? Are these like let's look at our hot loop. So we've got our current thing and we say byte pointer, blah, 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 blah. Okay, I think this might be just a little bit more compact, but just by using the return thing instead of break. I'm not sure, but we will try to do that. So, sure, let's just try and use that. So, got these two running. This is just too slow. Terminate that. We can try to rebuild this, and this will file, and we can run that now. Okay, so this is marginally faster. Or not. Okay, just okay. This is I'm at the limit of like what I want to optimize here. We could like stick around more, but I really don't care about that anymore. I'm just gonna let that cook, and I'll see you in a few hours. Bye-bye for now. Gonna mute myself, remove the camera. This is still gonna run, and hopefully we will see something some point.